Good evening, friends. Welcome to day 5 of the Six Sigma Masterclass Elite session. So, yesterday we looked at the types of data. So, data is broadly classified into two types, discrete data and continuous data. So, discrete data is the count data which can be expressed only in terms of whole numbers, and it cannot be expressed in terms of decimals or fractions. For example, number of participants in a training session, the number of units processed, the number of defects, etc., will be part of discrete data. Whereas continuous data is a measured data which can be expressed in terms of decimals or fractions apart from whole numbers. And continuous data, the examples are the length of a unit product, the weight of a unit product, and then time taken to process, and also the cost of a product, etc. So all these measurement dimension matrices will be part of continuous data metric. And then discrete data can be further classified as binary discrete data. So binary discrete data, we could understand that there can be only two options for a result, and binary discrete data will be expressed in terms of proportions. So just because the proportion will be a decimal value, we should not be straight away classifying it as a continuous data. So we need to look at the formula used for deriving that proportion value. If that formula fulfills the three conditions, then the data, the proportion data would be classified as binary discrete data, and the metric will be classified as binary discrete metric. So what are the three conditions? Both numerator and denominator should be count discrete. The numerator should be a subset of the denominator, and there should be only two options for a result, right? Then if you want to identify whether a data is discrete or continuous, I just gave you a hint, right? If you remember. So we need to look at the unit of measure. The unit of measure can be broken into different levels. Then it would be classified as continuous data. But if the unit of measure cannot be broken into different levels, then it would be classified as discrete data. And then we also understood that average denoted by lambda is the primary metric for representing the count discrete data. And if you are calculating the average for a count discrete data set, since average is also a derived value, we can get average in terms of decimals. But then what we are supposed to do, so if you are calculating average for a count discrete data set, we need to round it off to the nearest whole number. But then if you are calculating average for a continuous data set, even if the average is in terms of decimals, we can retain the decimal value as it is. Then we stepped into the statistics part. We looked at the descriptive statistics measures. There are two categories of descriptive statistics measures. One is the measure of central tendency and location. The other one, the measures of variation. Under measures of central tendency or location, which is also called as measures of average, we have mean, median, and mode. So mean is a simple arithmetic average, which is very easy for us to calculate. But the problem with mean is that it would get easily influenced by the presence of outlier or extreme value in a data set. So if you have an outlier or extreme value in the data set, which can happen due to assignable cost variation, then we need to use the metric called median. So how to calculate median manually? So median, we need to first and foremost arrange the data set in an ascending or descending order and pick the central value as median. But then if you have even number of data points, then there will be two central values. Then the average of these two central values will be median. Then mode is the most frequently occurring data point in a data set. So mode as a measure of average can be used if you are dealing with rank order data or rating data. Then similarly, measures of variation, we have three measures: range, variance, and standard deviation. So range is nothing but the difference between the maximum and the minimum values in a data set. So the problem with range is it doesn't consider any other value in between the maximum and the minimum values, and hence range as a measure of variation can be applied only if the data set contains six or less than six data points. So if the data set contains more than six data points, then we need to use either variance or standard deviation. So both variance and standard deviation would represent the average distance of each and every data point in the data set from the mean value. And another important thing that we could understand was both variance and standard deviation cannot take negative value, and the least value it can take is zero, provided all the data points in the data set are same, right? So standard deviation is one step further to variance, is a simplified version of variance, because standard deviation is the positive square root of variance. And we also looked at how to apply the Excel formula and perform all these calculations. And we also looked at an exercise wherein we applied the Excel formula to calculate the descriptive statistics measures. And we also solved or calculated all these measures using Minitab. Then we moved into the graphical representation of data. The first graphical format that we saw yesterday was histogram. So histogram is the appropriate graphical format to represent continuous data. So histogram will have a x-axis and y-axis. Along the x-axis, we will have the class intervals for the continuous data. And along the y-axis, we will have the scale for the frequency distribution. So frequency distribution is nothing but the number of data points in the data set that would actually fall in a particular class interval. So we will construct adjoining bars for each and every class interval coinciding with the respective frequency distribution. And once it is done, if you are going to connect the midpoints of all these adjoining bars, and if you are going to get a symmetric bell curve, then we can say that the data distribution is normal. But then case of presence of outlier in the data set, then we may get a skewed distribution, that is the bell curve having a longer tail, either on the right hand side or on the left hand side. So if it has a longer tail on the right hand side, we would call that as positively skewed, in which case the outlier value will be on the upper side of the data spectrum. But then if you have a bell curve which has a longer tail on the left hand side, we would call that as negatively skewed. So which would mean that the outlier value is on the lower side of the data spectrum, right? And then there are three things that we can identify by looking at a histogram. So first one is the spread of the data distribution. The second one is the shape of the distribution, whether the data distribution is normal or non-normal. And then the third thing is the class interval, which is likely to contain the average value. So the class interval that has the tallest bar is likely to contain the average value, because that class interval will have the maximum number of data points in the data set lying in between them. And then the only disadvantage with histogram is that it won't be able to capture the time orderliness of the data set. So we won't be able to recognize which data point occurred first, second, third, and so on. So if we want to maintain the time orderliness of the data set, then the best representation would be line chart. Yesterday or that we saw the objective of line chart as well, right? But then the second graphical format that we looked at was bar chart. So bar chart is the appropriate graphical format to represent discrete data. So if you want to represent proportions in a pictorial format, then we need to use pie chart. And then we looked at run chart. And we also understood that line chart is the simpler or the uh, simplest form of a run chart. So in case of line chart, we would be interested to know the trend of the process performance over a period of time. So if you want to plot the data over a period of time, or in other words, if you have the time zone along the x-axis, it could be on an hourly basis or on a daily basis or on a weekly basis or on a monthly basis, then the best representation irrespective of the data type would be the line chart. But in case of run chart, we will also have the average line at the center. And the main purpose of constructing a run chart is we would want to validate whether the data distribution is random or not. So only if the data distribution is random, we can infer that the process is influenced by common cause variation alone. And the process performance is also consistent. And we will be able to apply Six Sigma tools and techniques only if the process performance is consistent. On the other hand, if the data distribution is non-random due to any of the four non-random characteristics, that is trends, clustering, oscillation, or mixture, then we need to infer that the process is influenced by some assignable or special cause variation and the process performance is also inconsistent, right? So there are four rules that we would apply for identifying the presence of non-random characteristics in a data distribution. Number one, so if you observe six consecutive data points showing an upward or downward trend, then it would constitute non-randomness due to trend. Or if you observe eight consecutive data points lying either above or below the average line, then we will say that the data distribution is non-random due to clustering. Or if you find 14 consecutive data points alternating up and down the average line, we would call that as non-randomness due to oscillation. And finally, if you observe two sets of data points getting plotted at two different levels in a run chart, we would call that as non-randomness due to mixture. But then if you are going to construct run chart using Minitab, so we can look at this metric called p-value. The full form is probability value. So the criteria for p-value is that if it is greater than 0.05, then we need to infer that the data distribution is random. So we'll be looking at p-value for all the four non-random characteristics. And if the p-value happens to be greater than 0.05, then we will infer that the data distribution is random. But then if p-value is less than 0.05 for any of the four non-random characteristics, then we need to infer that the data distribution is non-random due to that specific non-random characteristic. And then finally, we looked at box whisker plot. So box whisker plot is the tool which would help us to identify the presence of outliers or extreme values in a data set, right? And case of box whisker plot, we will have the horizontal scale containing the data points arranged in an ascending order flowing from left to right, and just down below we will have the box plot constructed for that data set. So the box whisker plot will contain a rectangle box at the center with two whiskers or the horizontal lines extending from the either side of the rectangle box. So the entire box whisker plot will be segregated in terms of quartiles, meaning the distance between any two consecutive quartile points will be 25% of the data points in the data set. So the left extreme of the whisker will be Q0, which is the outlier limit on the lower side. And the left tip of the rectangle box will be Q1, which is the first quartile or the 25th percentile. The center of the box will be Q2, which is the second quartile or the 50th percentile, and the right hand tip of the box will be Q3, which is the third quartile or the 75th percentile. And finally, we will have the right hand tip of the whisker or the horizontal line, which will be Q4, right? So Q4 is the outlier limit on the upper side of the data spectrum, right? So what are these quartiles? As I told you, all these quartile points will be separated by distance of 25% of the data points in the data set. So the distance between Q0 and Q1 will be the first set of 25% of the data points in the data set. The second 25% will lie between Q1 and Q2, the third 25% between Q2 and Q3, and the final 25% of the data points will lie between Q3 and Q4. So Q0 and Q4 are the outlier limit values which we need to calculate by applying a formula, whereas Q1, Q2, and Q3, the quartile values can be ascertained from the data set. So when I say first quartile or 25th percentile, it means suppose we have 100 data points arranged in an ascending order. The value lying in the 25th position will be my Q1 value. Similarly, if you have 100 data points arranged in an ascending order, the value lying in the 50th position will be Q2 value. So this is the central value, and hence Q2 will be referred as median. And then if you have 100 data points arranged in an ascending order, the value lying in the 75th position will be my Q3 value. So Q1, Q2, and Q3 can be ascertained from the data set, whereas Q0 and Q4 needs to be calculated by applying a formula. And for calculating the outlier limit values, we need to have a metric called IQR, which is interquartile range. Interquartile range would represent the length of the rectangle box, so which can be calculated by applying the formula Q3 minus Q1. And then we can calculate Q0 and Q4. So Q0 will be a value less than Q1, as we can see in this diagram. So since the data set has been arranged in an ascending order flowing from left to right, so Q0 will be definitely a value less than Q1. So it will be Q1 minus 1.5 into IQR. 1.5 is the constant value here. And similarly, Q4 will be a value greater than Q3, and hence Q4 will be Q3 plus 1.5 into IQR. So once we have the outlier limit values calculated, then we can find out whether the maximum and the minimum values in the data set fall well within the outlier limit values. If that is the case, we can infer that there are nil outliers in the data set. But then if you have any data point which is either below Q0 value or above Q4 value, then those data points will be termed as outliers or extreme values. And we also worked out using the box whisker plot logic, right, for this processing time data set. And we also saw how to construct the box whisker plot using Excel as well as Mini tab. So if you are constructing the box whisker plot graphically, so we can find out the presence of outlier very easily. You don't have to really perform all these calculations. So you just need to find out if there is any dot appearing in that box whisker plot. So if dot is not there, then we can infer that the data set doesn't contain any outlier value. But then if you find any dot appearing in the box whisker plot, then we can identify or infer that this data set contains an outlier value. So if you can keep the cursor on top of the dot, so it will let you know which value has been considered as outlier by box whisker plot, right? So this is about the box whisker plot calculations. And we also kind of looked at an exercise which is likely to come as a question in the final assessments. So here we were asked to calculate the outlier limit on the upper side. So outlier limit on the upper side is nothing but the Q4 value. And I also, showed you how to input the values in this template and then get the answers. So you just need to arrange the data set in a vertical structure. That's it. You don't even need to sort this in an ascending order. So when we are applying the Excel formula to perform the calculations, there is no need for us to sort the data set in an ascending or descending order. The Excel will take care of all these things at the back end. Only if you are going to solve this manually, then we need to arrange the data set in an ascending order and then perform all the calculations. So applying the Excel formula, we don't have to really sort the data set in an ascending order. So we can just enter the values as given in the question, the same sequence. But only thing is we need to enter the values in a vertical structure. So that's the only condition here. And once we do that, we can see the answers getting populated automatically in the output section. So once you have finished entering all the values in the input data column, then we can pick the relevant answer from this output section. So if they want you to calculate the Q0 value, then the answer is there. Or if they want you to calculate the IQR value, we have the answer here. So whatever metric they ask you to calculate in that question, so we can pick the relevant answer from this output section. And then finally, we also looked at this exercise number 3. So this is a logical question. So it doesn't involve any calculation. So the IQR for a data set has been given. So this is nothing but the marks scored by the students in a class. So the IQR value is given as 80 minus 40. So which would mean that the Q3 value is 80 and Q1 value is 40, right? And with this information, we have been asked to estimate the percentage of students who have scored more than 80 marks. So when you say more than 80 marks, we are looking at the area beyond Q3 in a box whisker plot. So the percentage of data points that would lie beyond Q3 in a box whisker plot is 25%, which we can pick as the right option, right? So yesterday, we missed out solving this exercise using our AI tool. So let us actually, perform the descriptive statistics calculations using the AI tool. So let me copy paste the entire table.
Hi, Sridhar, I have a question.
Yeah.
So yesterday when we were doing the exercise with the given data set, uh,
Mm,
that's processing time, and we were
mm,
calculating, Q0, Q4, and IQR as well.
mm.
All those values are showing within the, limit there.
Yeah.
It was not going too far from
Mm,
that particular. However, when when we did the second exercise, it
mm,
actually showed up a huge variance.
mm,
The maximum value shows 16, however, the Q4 shows 33 and
mm,
Q0 shows minus 15.
mm, mm.
Uh, I got confused on this.
No, no. What is your question?
So the question is the outlier,
Mm.
which is going too high or too low.
No, 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 no. This is not outlay. This is outlay limit. So meaning we can have data points up till 33, right? So till
Okay.
33, we will not call any of these, data points as outlier. Similarly, on the lower side, it can go up to minus 15. So till
Oh,
it
okay.
reaches minus 15, we will not call any data point as an outlier in this data set. That's the meaning of it.
Oh, okay.
So this gives you the flexibility to go
Okay.
up to that extent.
All right. All right. All right. So
Okay.
once the value goes beyond 33,
Yeah.
that will
33
be
or it's less than minus 15, we will call those values as outliers.
outliers. Okay.
Yeah.
All right. Thank you.
Yeah. So we will see how to use the perplexity tool to perform the calculation. So I've just copy pasted the entire table and I have just given the prompt as calculate the descriptive statistics measures and I press enter. So it will read the attached file and then it will come up with the answers. Right? So it gives you the Q1 value, the minimum value, the maximum value, the variance, right? So these are some of the statistics measures, standard deviation, right? So range is zero point 0.4, right? Interquartile range, IQR is zero point 0.2. So mean is 5.2, median is also 5.2, right? So some of the key descriptive statistics measures, right, are provided here for this particular scenario. So you can also use the AI tool to perform all these calculations. So side by side, apart from solving all these problems using Minitab, some of the problems we will use the AI tool and see how to perform the calculations, right? But then, as I told you on the very first day, we cannot fully depend on this AI tool. Some of the basic tools, they don't really provide the right answer. So there is a risk in being fully dependent on the AI tool. So some of the advanced AI tools can perform the calculations correctly and provide the right answers. But then some of the basic AI tools I've seen, they don't really provide the right answer. So we need to be slightly careful. So we still cannot be completely dependent on these AI tools. We need to probably, you know, kind of uh, trust our natural intelligence, right? That is much more safer than trusting the artificial intelligence. So we can just take a clue, as I told you, for any scenario where you are getting stuck, you don't know how to proceed further. So probably can get a clue or a hint from the AI tool, but then you need to verify and validate yourself as to whether those scenarios are valid for the kind of business problem that you are currently facing. So for that, we need to use our natural intelligence to come up with the final decision. Fine. So in short, what I'm trying to say is AI tools can be used as a complementary tool, not the the only tool to provide us with the final answer. Fine. So let us look at the final exercise under descriptive statistics measures. Anyway, this exercise is not going to come as a question in the final assessment, but then this is something that we need to know how to approach and how to come up with the final inference, right? So this is a very interesting exercise. The time taken to open a bank account for a couple of branches A and B of bank XYZ is as given below for 30 customers. So out of the two branches, kindly evaluate which branch provides a better performance. So we have been provided with the time taken to open a bank account for both branch A and branch B of bank XYZ, right? So if you want to evaluate which one is a better performing branch, what is that we need to do? So the first approach obviously will be to
Mean,
calculate the mean time. Very
yeah,
good. So we need to calculate the mean time taken to open a bank account. So since we are talking about time here, so whichever branch is taking a lesser mean time to open a bank account, that branch will be considered as a better performing branch. So that will be my first approach, right? So let me just, provide that summary here. Since we need to evaluate better performing branch, we will calculate the mean time taken to open a bank account by both branch A and branch B, right? So whichever has a lesser mean time, so that branch will be considered as better performing branch. So let me give the title as mean time, and then we have branch A and branch B. Right. So let me apply the formula here. So what is the formula? Is equal to average, and then provide the range of the data set. This is for branch A, right? Similarly for branch B is equal to average, and then provide the range of the data set. Right. So the mean time taken to open a bank account seems to be the same for both the branches. It is 2.5 hours for both branch A and branch B. So we will not be able to take a final decision with regard to a better performing branch by looking at the mean time. So the mean time is pretty much similar for both the branches. So what is that I need to do next? So now that the mean time is same for both the branches, so what should be my next step? Any idea? So which metric I need to actually look at?
median,
No, median will be considered only if the data set has an outlier. So mean, median, they're all measures of average, right? So you don't have to, calculate both of them. So it will be either mean or median. So median as a metric can be applied if the data set contains some outlier value. So I don't find any outliers in both these two data sets. So that is why
okay.
we calculated the mean time. So mean is same. Then what is the next step that I need to adopt?
Variance or standard
Yeah,
deviation.
fantastic. So variance or standard deviations. I need to look at the consistency in the performance. Now that the average performance is pretty much the same for both the branches, the next step would be to look at the consistency in the performance, right? So based on the consistency, I will take a final call as to which one is a better performing branch. So if you are talking about consistency, we need to calculate the variation metrics. So we will calculate standard deviation, right? So standard deviation will let us know which one is a better performing branch, in the sense which one is more consistent in its performance, right? So standard deviation is less. It means the consistency demonstrated by that particular branch is very high, right? So lesser the variation, higher will be the consistency. So lesser the standard deviation value. So we can infer that the particular category is demonstrating higher consistency in its performance, right? So that's the next step. So since the mean time taken to open a bank account is same for both the branches, we now need to look at the consistency, the performance to evaluate better performing branch. So we will calculate the standard deviation and the branch that has a lesser standard deviation value will be considered as better performing branch, right? So we will calculate the standard deviation. Let me just copy paste this format. So instead of mean time, I'll be calculating the standard deviation. So what is the formula we need to apply for calculating the standard deviation is equal to stdev dot s and provide the range of the data set. So this is for branch A, and then I need to calculate for branch B, stdev dot s, and then provide the range of the data set for branch B. Right. So as we can see, branch B has a lesser standard deviation value compared to branch A. So branch B seems to be much more consistent in its performance compared to branch A, and hence we can infer that branch B is a better performing branch compared to J. So since branch B has a lesser standard deviation value compared to branch A, we can infer that branch B's performance is much more consistent compared to J, and branch B can be considered as better performing branch, right? So branch B can be considered as better performing branch. What we can also do is construct a box whisker plot. So we will have multiple box whisker plots, right, constructed because we have two categories of data sets. So first we need to highlight both these data sets and then go to insert, and then under recommended charts, the one with all these bars, down below we find the box whisker plot. So you can see two box whisker plots placed side by side. So the blue color one pertains to branch A and the red color one pertains to branch B. So blue is branch A and the red color one is branch B. So the length of the box whisker plot will give you a clear-cut indication with regard to the variation exhibited by that category, right? So here we find the length of branch B's box whisker plot is significantly lesser compared to that of branch A. So the data spread is somewhat higher, then obviously we will have a box whisker plot which is slightly higher in length, right? So here we find branch A's box whisker plot is lengthier compared to that of branch B, or branch B's box-Whisker plot is the length is much smaller compared to that of branch A. So we can clearly identify that branch B's variation is much lesser compared to that of branch A. And that is why we get the standard deviation value as zero point 0.3 against zero point 0.8 for branch A, right? So this is clearly coming out in this box-Whisker plot as well. So when we place them side by side, we can clearly understand that the branch B's box-Whisker plot, the length is significantly lesser compared to that of branch A, which would give you a clear-cut indication that the variation exhibited by branch B is comparatively lesser, right, than branch A. That means the branch B's performance is much more consistent compared to branch A, right? So this is another advantage that we get when we construct the box-Whisker plot. So box-Whisker plot as a tool will also help us to logically subgroup the discrete x's. What are the discrete x's here? The two categories that we are talking about, branch A and branch B, are the discrete x's. So box-Whisker plot will help us to logically subgroup discrete x's against continuous y. So what is the continuous y? The continuous y is nothing but the time taken to open a bank account, right? So this is another benefit that we would get when we construct this box-Whisker plot. So we can also look at subgrouping the discrete x's against the continuous y. So that is what is written here. So there can be a question on this. So that is why I'm making this point. So box-Whisker plot as a tool can also help us to logically subgroup discrete x's against continuous y, right? So they will ask you which tool will help us to logically subgroup discrete x's against continuous y. We need to pick the option box-Whisker plot. Fine. So this is about the descriptive statistics and the graphical representation of data. So these graphical formats can be constructed for us to come up with the final inferences. So it becomes so easy. So you don't even need to perform any calculation, just construct the appropriate graphical format in order to come up with the final inference. So even the box-Whisker plot, as I told you, you don't have to necessarily perform all those calculations, right? So we learned how to perform the calculations, but in a practical scenario, so you don't have to really perform all those calculations. You can simply construct the box-Whisker plot in Excel. So if at all there is any outlier value present in a data set, as I told you, it will get indicated through that blue color dot or whichever is the color of the box-Whisker plot. So the dot also will be the same color. So moment you find a dot in the box-Whisker plot, we can understand that the data set contains some outlier value. And if you're going to keep the cursor on top of that dot, then it will let you know which value has been considered as outlier by the box-Whisker plot. Fine. So let us proceed further. Next, we are going to look at concept of yield. This is a very small section. So let me put today's date, which is 13th of Jan 2026. Right. So concept of yield. So we'll be asked to solve what is called as roll throughput yield. So we need to be aware of this metric. So we'll be asked to solve roll throughput yield for a given process. But before that, we need to understand certain terminologies. First and foremost, what is the yield, right? So yield is the accurate output generated by a process. So yield is the accurate output generated by a process. So even if you are going to make correction, right? So that will be counted as part of the yield, right? So it's an accurate output which is kind of generated by the process. And then we have a metric called throughput yield. So what is a throughput yield? So throughput yield is the first pass yield generated at a sub-process level. So throughput yield is the first pass yield generated at a sub-process level. So within a process, you may have multiple sub-processes. So if you are going to calculate the first pass yield of these multiple sub-processes, that first pass yield is what we would call as throughput yield. So throughput yield, first pass yield, both mean one and the same. So when you talk about throughput yield, we are talking about the first pass yield at a sub-process level. And then we have what is called the roll throughput yield. So roll throughput yield is the first pass yield at a process level. So we will be calculating the roll throughput yield for the entire process. So throughput yield as a metric will be calculated at a sub-process level, but roll throughput yield will be calculated at a process level. So roll throughput yield is the first pass yield at a process level. So how to calculate this roll throughput yield? So we need to simply multiply the throughput yield values that we would have obtained for the multiple sub-processes. That's it. So you will get the roll throughput yield. Suppose the throughput yield values are given as percentage values in the question. So what is that we are supposed to do? So we need to first and foremost convert those percentage values in terms of decimals and then simply multiply them to get the roll throughput yield, because you'll be asked multiple questions to calculate the roll throughput yield for a given scenario. So they would have given the throughput yield values for the various sub-processes as percentage values. So if you are provided with percentage values as throughput yield, then what is that we need to do in order to calculate the roll throughput yield? So we need to first and foremost convert all those percentage throughput yield values in terms of decimals and then simply multiply them in order to get the roll throughput yield for the entire process. So that will be a decimal roll throughput yield value. So that decimal roll throughput yield value can always be converted in terms of a percentage value. So let us look at an exercise for RTY calculation. So we'll click on the next sheet, run chart and RTY. So run chart we already seen. So let us look at exercise number 2, which is RTY calculation, the roll throughput yield calculation. So calculate the roll throughput yield percentage for the below data. So this is process XYZ and we have 4 sub processes under this process, and we have been provided with the base data with regard to number of items processed and also the number of items without any defect. So we can calculate the first pass yield or the throughput yield for this for all the 4 sub processes. Right? So you can calculate the first pass yield or throughput yield for all the 4 sub processes. But then the final assessment, you would be given the throughput yield values, as I told you, right? There is no need for you to calculate the throughput yield values as we are doing here. But in the final assessment, you'll be provided with the throughput yield values, but those will be percentage values. So what is that we are supposed to do? We need to convert all those percentage values in terms of decimals and simply multiply them to get the roll throughput yield in decimal. And that decimal roll throughput yield value can be converted and expressed in terms of percentage, right? So let me perform the calculation. So first pass yield will be the number of items without any defect of a particular sub-process divided by the total number of units processed by that sub-process. So I can just copy paste this formula for all the other 3 sub-processes. So we get the throughput yield value as 0.95 or 95% for all the 4 sub-processes. So even for the other 3 sub-processes, if you are going to round it off to 2 decimal places, then we'll get the answer as 0.95. So it is 0.95 as the throughput yield value for all the 4 sub-processes. So we simply need to multiply them to get the roll throughput yield for the entire process. So I'm going to multiply the throughput yield values of all the 4 sub-processes. That's it. Right? So I get the roll throughput yield as a decimal value. So this can always be converted as a percentage value. That's it. Right? 81.4% is the correct answer. Or if you want to use the template, we just need to provide all these throughput yield values for the various sub-processes in decimals. That's the only condition. You'll automatically get the roll throughput yield expressed as a percentage value in the output section, right? So let me just give reference to these throughput yield values. Sub-process T, right? So you get the RTY as a percentage value straight away. So you don't have to really convert the decimal RTY value in terms of percentage. Only thing is, when you input the throughput yield values, please do not enter it as a percentage value, enter it as a decimal value. So 87% will be written as 0.87. 89% will be 0.89, 92% will be 0.92. So that's why I told you yesterday. So we need to be comfortable converting the decimal value in terms of percentage and also the percentage value in terms of decimals, right? So once we convert all these throughput yield values in terms of decimals, we can simply enter them in this template and we'll get the percentage value for the roll throughput yield, and we can pick the right option from the multiple choice because the multiple choice will contain the percentage values for the roll throughput yield, right? So you can pick the right option from there. So very simple calculations, very simple exercise as well, right? The next one that we are going to look at is a very, very important chapter, measure phase. In fact, even when you execute your routine process, this exercise is something that we need to perform on a routine basis, right? So it's not as if this exercise has to be done only at the time of working on a Six Sigma project. So this is something that we are supposed to do on a routine basis. So the exercise name is measurement system analysis. So in short, it is referred as MSA, right? Measurement system analysis or MSA. So this MSA, why do we need to perform this MSA exercise is the question, right? So we have collated the base data for the CTQ metric. So we are going to calculate the CTQ metric by considering all those base values that have been given to us by the process team. Now, how do you know that the base data that has been handed over to us by the process team is absolutely valid, right? So if you're talking about the accuracy percentage, then we need to be dependent on the decisions provided by the quality inspectors because quality inspectors will inspect a sample unit and then finalize whether that sample unit is defective or non-defective. So based on the count of defectives they provide, so we will calculate the accuracy percentage and project the same to the leadership team. But then how do we know that the quality inspectors are taking the right decision with regard to the sample unit being defective or non-defective, right? So there will be a question mark whether the data provided by them is valid, right? So in order to uh, you know confirm the validity of the base data that we would collate for populating a metric. So it's always better to perform this measurement system analysis exercise. Similarly, say you have some measurement values collated. So how do you know that whatever measurement values I have collated is absolutely valid, right? Say for example, you're using a stopwatch in order to calculate the time taken to process a unit item. So whatever time values you have entered, so how do you know that the stopwatch has given the right, time value? Or you have measured the weight using a weighing scale. So how do you know that the weighing scale has provided us with the correct value? So there will always be a doubt. So we need to perform this exercise called measurement system analysis. In fact, measurement system analysis is the first activity that we will perform as part of the measure phase. So there can be a question on this. So which activity will be performed first as part of the measure phase? So you need to pick the option MSA from the multiple choice, right? So this will be the first activity that will be performed as part of the measure phase because it's important for us to validate the correctness of the base data that we have collated for the CTQ metric before proceeding with the advanced analysis, right? So the base data itself is not valid, then there is no point in performing analysis with the data because that will always lead us into the situation called GIGO situation. We should not forget garbage in, garbage out kind of a situation. So from that perspective, this particular exercise becomes all the more important and critical, right? So as I told you, so you might be projecting uh, the metric performance, the key metric performance month on month, right, to your leadership team. So you'll be presenting the metric dashboard. But how are you sure that whatever numbers you are presenting to your leadership is absolutely correct? Fine. So unless and until we perform this exercise, we cannot be 100% confident that whatever numbers we are presenting to our leadership is absolutely correct. So if you're painting everything in green, leadership also will feel very, very happy about your performance. But do they know that, this is the correct, metric value that you are presenting to them, right? So there will be a question mark on that. So in order to, feel confident that whatever numbers I'm presenting to the leadership on a month-on-month basis is absolutely correct. So we need to perform this exercise on a routine basis, right? At least once in a quarter. So that's why I told you. So this is something that we will not perform just at the time of working on a Six Sigma project. We need to perform this on a routine basis so that you will not face any surprises during a Six Sigma project exercise. Just imagine this scenario. So as part of Six Sigma, this is a mandatory exercise, right? So when you perform this MSA exercise during the Six Sigma project exercise, and if you happen to find out that the measurement system is not working fine, so what is that we are supposed to do? We cannot obviously trust the data provided by that measurement system. So we need to discard the entire data provided by that measurement system, correct the measurement system, and then collate the data all over once again, which will only result in delay in completion of the project exercise, and the leadership is not going to be happy about it. But then if you have been performing this exercise on a routine basis, so when we actually perform the same exercise as part of our Six Sigma project, you can be rest assured that the measurement system is working fine and whatever data the measurement system has given is absolutely valid, right? So you don't have to really worry about the result of this exercise, right? So if you have been performing this exercise on a routine basis. So that's the thing. So it's always important for us to perform this exercise on a routine basis so that even if you find the measurement system not working fine, so we can always, correct the measurement system before we start working on these kind of Six Sigma projects, right? So, so that's what I've written here. So MSA is supposed to be performed on a routine basis, not just at the time of a Six Sigma project exercise. Now, what would constitute the measurement system for a discrete data as well as continuous data? Again, MSA, we have separate exercises that can be performed for a discrete data scenario and also for a continuous data scenario. So if you are dealing with discrete data, so it will be called as discrete data measurement system analysis. And what would constitute the measurement system if it is a discrete scenario? So the quality inspectors would be inspecting the sample unit and then coming up with a decision as to whether the sample unit is defective or non-defective will be a part of the measurement system. In fact, they will be the only part of the measurement system, right? So the quality inspectors will be the only part, right, with which would represent or who would represent the measurement system, right? So in short, for a discrete data measurement system analysis, the measurement system would consist of only the quality inspectors. So they alone will be part of the measurement system. But in case of continuous data measurement system analysis, since we would be dealing with all these measurement values, so how will you get these measurement values? You need to measure them using some measuring equipment. And who will handle these measuring equipments? There has to be some appraiser who needs to handle these measurement equipments and then measure the unit item. So in case of continuous data measurement system analysis, so there will be two entities which will be part of the measurement system. So one is the measuring equipment that we would consider for measuring the unit item, and the other one is the appraiser who would be handling the measuring equipment in order to measure a unit item. So these two entities will be part of the entire measurement system as far as continuous data is concerned. So discrete data is all about the inspection activity. So only the quality inspectors will be part of the measurement system. But in case of continuous data, we will be handling a measuring equipment and then measuring the unit item. So the measuring equipment as well as the person who handles this measuring equipment, so this person will be called as an appraiser. So both will be part of the entire measurement system. Clear? Now, how to find out whether the measurement system is working fine or not? Now, how to validate? Because I told you that unless and until the measurement system is working fine, we cannot proceed further with the data provided by that measurement system. So the measurement system happens to be not working fine, then we need to discard the entire data provided by that measurement system, correct the measurement system and collate the data all over once again. But how are we to find whether the measurement system is working fine or not? So for that, we need to look at the variation contributed by the measurement system, right? So if you look at a high level process, so how it will appear? So we will have the input which will be fed into the process, which will come out as an output, and this output will get measured, right? And we will have the measurement values. Correct? So this is the procedure. So input will be fed into the process and then we'll get the output. The output will get measured and we will have the measurement values collated for this output, right? So if you are going to inspect the output, then we will have the details with regard to how many defectives are there, how many non-defectives are there, etc. But then if you are measuring time for the output produced, then we will have the time data. Or if you are measuring weight of the output produced, then we will have the weight measurements, listed down here as the data set. Now, whatever, say for example, you are measuring weight. So we will have, say, weight as 2.58, 2.54, 2.55, etc. Now, whatever differences you find in these measurement values after measuring the output will be called as the total variation. So the differences that you would find in the final data set containing the measurement values is what we would call as the total variation. And this total variation will be a combination of the process variation as well as the measurement system variation, right? So when we actually measure the output, so whatever values that we would get, and if you find the differences in the measurement values, so this is what we would call as the variation in the final data set, and that will be my total variation. So total variation can be split as combination of process variation as well as the measurement system variation. So the process here would have contributed to some variation in this data set, right? Which is quite obvious. Also, when we measure the output, the measurement system also would contribute to some amount of variation in the final data set, right? So the process would contribute to some quantum of variation. The measurement system, because the output is getting measured, and then only we are going to list down all these values. So obviously the measurement system also will contribute to certain quantum of variation in this final data set. And the variation that you would observe in the final data set is what we would call as total variation. So total variation can be split as process variation and measurement system variation. But then the Six Sigma project, our effort will be to reduce this process variation. Is it not? So in a Six Sigma project, we'll be totally focused on improving the process efficiencies, meaning we will be focused on reducing the variation contributed by the process. And for that, we need to ensure that the variation contributed by the measurement system is as minimum as possible. So then only we can say that the measurement system is actually working fine and we can go ahead with our analysis and then try to reduce the process variation as part of our Six Sigma project exercise. Clear? Right? So this measurement system is something that we need to validate. So how will you find out that the measurement system is working fine? So we need to look at the variation contributed by the measurement system. And if the variation contributed by the measurement system is well within a certain criteria limit, then we can infer that the measurement system is working fine and we can trust the data provided by that measurement system for further analysis, with which we would be able to reduce this process variation as one of the goal of our Six Sigma project exercise. Clear? So this is how we will proceed further. So this measurement system variation or the variation contributed by the measurement system should be ideally less than 10%. So if you find the measurement system variation being more than 10%, then we need to infer that the measurement system is not working fine. There is some fault with the measurement system, and we need to correct the measurement system and collate the data all over once again. So that is what I have written here. So in a Six Sigma project, our focus will be to reduce the process variation, and for this, the measurement system variation should be as minimum as possible. So should be well within the criteria limit of 10%. So the total variation is equal to process variation plus the measurement system variation. So in a Six Sigma project, our effort will be to reduce the process variation. For that, the measurement system variation should be less than this 10% criteria limit. So if it is greater than 10%, then we need to discard the data provided by that measurement system, correct the measurement system, and collate the data all over again, right? So we are going to look at how to perform discrete data measurement system analysis. The name for this exercise is attribute gauge R&R agreement analysis. Attribute is the other name for discrete. So we need to remember this. Attribute is the other name for discrete. So the name of the discrete data measurement system analysis is attribute gauge R&R agreement analysis. What is R&R? We will know in a short while, right? So this exercise will be performed using the manual formula. So we will calculate the matrices, the performance of the matrices, which would actually represent the measurement system variation for a discrete data scenario, and then see whether the variation percentage of these matrices is less than 10% or not, right? So there are multiple matrices that would actually represent the measurement system variation for a discrete data scenario. But then if you are going to solve this exercise using Minitab, so we need to look at a metric called kappa value. So apart from the usual matrices that you will see, right? So we will learn about those matrices in a short while. So in Minitab, we'll also look at another metric called kappa value. So what is the criteria for kappa value? Just like your p value, this kappa value is one of the metric, right? Provided by Minitab. So the criteria for kappa value is that it should be ideally greater than 0.9 for all the measurement system variation matrices. Then only we can say that the measurement system is working fine. But if the kappa value is between 0.75 and zero point 0.9, then we can marginally accept the data provided by the measurement system with necessary approvals given by the leadership team. So there can be a question on this in the final assessment. So they would have given the kappa value as 0.87 and they will ask you to infer. So we need to pick the option that we can marginally accept the data provided by the measurement system with necessary approvals given by the leadership. So that is the correct option that we need to pick. On the other hand, if the kappa value for any of the measurement system variation metric happens to be less than 0.75, so we straight away need to discard the data provided by the measurement system, correct the measurement system, and collate the data on over once again, right? So this entire exercise will be segregated into two parts. One is performing the exercise as such, right? Performing the measurement system analysis exercise as such. And the second part is calculating the measurement system variation metric performance. So what is the variation percentage with regard to all these matrices that would represent the measurement system variation. So that variation percentage for all the multiple matrices should be less than 10%. Then only we can say that the measurement system is working fine, and we can also trust the data provided by that measurement system. So let us look at how to conduct this exercise. So as I told you, this exercise is called as attribute gauge R&R agreement analysis. Attribute is the other name for discrete. So I've given detailed steps as to how to conduct this exercise and how to calculate all these measurement system variation matrices. So the name of the exercise is attribute gauge R&R agreement analysis. So this is the discrete data measurement system analysis. So since the discrete data would deal with the quality inspection activity, so we need to have minimum of 30 samples considered for this exercise. So we need to have minimum of 30 samples considered for this exercise. And these samples should be a proper mix of both defective and non-defective samples. So we should not have all the 30 samples as non-defective, and we should not also have all the 30 samples as defective. So we need to have a mix of both defective and non-defective samples, right? And then we will have minimum of two auditors. So whatever numbers I'm providing here, these are all the minimum numbers that we need to consider for performing this measurement system analysis exercise. So we need to have 30 samples with a proper mix of both defective and non-defective samples, number one. Number two, we need to have minimum of two auditors or quality inspectors involved in this exercise. That is the second condition. Number three, each auditor will be subjected to two trials, right? So each auditor will be subjected to minimum of two trials. So we can have any number of samples, we can have any number of auditors or quality inspectors involved in the exercise. We can also have any number of trials, right, performed by each and every auditor. But whatever I'm quoting, these are the minimum numbers that we need to consider for performing this exercise. So we need to have minimum of 30 sample units with a proper mix of both defective and non-defective samples. We need to have minimum of two quality inspectors or auditors, and we need to have minimum of two trials conducted by both the auditors, right? So this is the minimum requirement for us to perform this measurement system analysis exercise for discrete data, which is also called as attribute gauge R&R agreement analysis. So both the auditors will actually inspect all the 30 sample units for the first time. So that is what we would call as trial one. And they will also provide the results. So how to interpret these results? So when they say accept, it means the sample unit is non-defective. When they say reject, it means the sample unit is defective. Again, I repeat, when they say accept, it means that the sample unit is non-defective. So when they say reject, it means that the sample unit is defective. Clear? So that is the meaning of accept and reject. So the auditors will perform the trial one exercise, wherein the first round they will inspect all the 30 sample units and then come up with their decision. And then after some time, they will perform the trial two exercise. So trial two, they will once again inspect all these 30 sample units independently. Independently means when they perform the trial two exercise, the auditor should not remember the result that he actually gave for trial one for a particular sample. So if that auditor is going to remember the result he actually gave for trial one for a particular sample, then the auditor, without even inspecting second time, so he may even replicate the same result as the trial 2 result. So which has to be avoided because we want the auditors to, inspect for the trial 2 exercise. So we don't want them to remember the results they gave for the trial 1 exercise and replicate the same result for trial 2. No, not like that. So we want them to inspect all these 30 samples once more for the trial 2 exercise, right? So there should be sufficient time gap between trial 1 and trial 2. Say a 1 week gap, right, is more than sufficient so that the concerned auditor will not remember the result that he gave for the trial 1 exercise for a particular sample when he is performing the trial 2 exercise, right? So the trial 2 exercise also will be done independently and the auditor will provide the results for all the 30 samples. So these are the trial 1 and trial 2 results that we have collated for both auditor 1 and auditor 2. And apart from the auditor provided results, we will also collate what is called subject matter expert result, SME result, right? So whatever be the measurement metric, right? There has to be some kind of a reference value which we need to trust. Only if we have the reference value, we will be able to validate whether the measurement value that we have actually measured is correct or not. Say, for example, so how will you know that your clock at home is showing the right time or the watch is showing the right time? So how will you know that your watch is showing the right time?
It will match with other watch, maybe
No, other watch also can be faulty, right?
look into the TV or maybe
Yeah,
system.
yeah, that's the thing that you'll do, correct? So you
Yeah.
look at some electronic items. You can look at your mobile phone, you can
Mm.
look at your laptop, or you can look at your television set. And the time displayed by these electronic items will be considered as the true value or the reference value.
Yeah.
Based on that, you'll be able to say whether your watch is running fast or slow or showing the correct time, etc. Right? So we need to trust that value. So the time displayed by all these electronic items, we need to definitely trust them as the correct value, right? Because then only we can treat that as a reference value and then find out whether our watch is showing the correct time or not. Similarly, in this exercise, we need to have a true value or a reference value which needs to be trusted. And for that, I'm going to collate the SME result or the subject matter expert result for all these 30 sample units, right? So the SME will also independently perform the inspection exercise covering all these 30 samples and will provide the results. So the results provided by the subject matter expert will be considered as the true value or the reference value based on which we will be able to find out whether the auditors have provided an accurate result for a particular sample unit. So the accuracy part can be calculated only when we have this SME result or the subject matter expert result, which will be considered as the true value or the reference value. So once this exercise is conducted and we have collated all these input values, now is the time for us to perform the analysis and calculated some three matrices which would actually reflect the measurement system variation for a discrete data scenario. So what are the three matrices? The first metric is called as repeatability. The second one is reproducibility. And the third one is accuracy. So repeatability and reproducibility is the expansion of R and R here, the title. So when I say gauge R and R, so gauge is normally considered as a measuring equipment, right? So when I say gauge R and R, we are talking about repeatability and reproducibility, right? And we also have third metric, accuracy. So all these three matrices, which would actually represent the measurement system variation, the variation percentage should be less than 10%. The variation percentage is going to exceed 10%, then we need to infer that the measurement system is not working fine and we need to discard the data provided by that measurement system, correct the measurement system and collate the data on our once again. So all these three measurement system variation matrices, we need to have the variation percentage less than 10%. Even if one of the three matrices that we are seeing has a variation percentage in excess of 10%, then we cannot proceed any further. So we need to infer that the measurement system is not working fine. So probably the quality auditors in the discrete data measurement system analysis are not providing with the correct result, right? Are not coming out with the correct result. So we need to look at where the auditors are making mistakes, and we need to conduct some focused training for them so that they get properly oriented on the part of the process where they may have some difficulty in comprehending, right? So this is a corrective action that we will take once we find out that the measurement system is not working fine. So for this exercise, let us, calculate all these three, measurement system variation matrices. So for that, I'm going to create some space, right? Right. So first I'm going to calculate repeatability. So before that, what exactly is repeatability? So repeatability is nothing but the consistency in the auditor provided trial results for a particular sample. So repeatability is nothing but the consistency in the auditor provided trial results for a particular sample, or consistency in the results provided by an auditor for multiple trials for a particular sample. So we can have either two trials or more than two trials as well, right? So minimum we need to have two trials. So only when we have two trials conducted, we can even calculate this repeatability metric. Clear? So this is nothing but the consistency of the results provided by an auditor for multiple trials for a particular sample. So auditor 1 has given the trial 1 result as accept for sample 1, and the trial 2 result also as accept for sample 1. So it means auditor 1 scores on repeatability as far as sample 1 is concerned. But then if you look at auditor 2, so trial 1 for sample 1, he says reject, whereas trial 2 for sample 1, he says accept. So there is a mismatch in the trial results provided by auditor 2. So this would actually constitute repeatability mismatch or repeatability variation. And this repeatability variation percentage that we would calculate should be ideally less than 10%, right? So as I told you, even if one of the metric, like either repeatability or reproducibility or accuracy, has a variation percentage in excess of 10%, then we need to infer that the measurement system is not working fine. So all the three matrices, the variation percentage or the mismatch percentage should be less than 10%. Clear? Right? So that is the criteria. But then all these three matrices are pretty much interlinked. So even if you have repeatability in excess of 10% variation, it's quite likely that reproducibility and accuracy variation also would be more than that 10%, right? So let us find out, let us calculate all these three matrices. Anyway, we will also look at reproducibility. So what is reproducibility? So reproducibility is nothing but the consistency of results provided by multiple auditors for a particular sample. So auditor 1 and auditor 2 should have given the same result for a particular sample for them to score on reproducibility. So in case of repeatability, we are looking at the consistency of the results provided by an auditor for multiple trials, right? But for reproducibility, we are going to compare the results provided by multiple auditors for a particular sample. So here in this case, we have only a couple of auditors. So both the auditors put together, we will have four trials. Trial 1 and trial 2 for auditor 1. Similarly, trial 1 and trial 2 for auditor 2 for a particular sample. So all the four trial results provided by both the auditors should actually match. Then only we will call that as reproducibility match percentage. So that will be considered for the reproducibility match percentage. Even if there is a small variation or a small mismatch, even if one of the trial results is different, then we will say that it is a reproducibility mismatch or reproducibility variation. So as far as sample 1 is concerned, auditor 2 trial 1 result is not matching with the other 3 results. So this would constitute reproducibility mismatch or reproducibility variation. But then if you look at the fourth sample, both the auditors for both the trials, they are given the same result. So you're not looking at the correctness of the result here. You're only looking at the consistency of the results provided by multiple auditors. So all the 4 results are reject. So the auditors will score on reproducibility as far as sample number 4 is concerned. Right? So this is how we will measure reproducibility, and thereby we will also measure the reproducibility mismatch or reproducibility variation. And then the final metric that we have is accuracy. Accuracy is nothing but the consistency of the auditor provided results when compared with the true value. So here we will be comparing the auditor 1, trial 1 and trial 2 results with that of the SME result. So all these 3 results should actually match for that auditor to score on accuracy. So even if there is a single mismatch, so it would amount to accuracy variation. And all the 3 matrices, as I told you, the variation percentage or the mismatch percentage should be ideally less than 10%. So if you have the mismatch percentage or the variation percentage in excess of 10%, then what is the corrective action you need to perform? So we need to discard the data provided by that measurement system, correct the measurement system, and collate the data all over once again, right? So let us calculate all these 3 matrices, specifically the variation percentage. Repeatability is a metric in a positive sense. That means the matching percentage has to be projected as repeatability. So to what extent an auditor is able to repeat the same result that he gave for trial 1 for trial 2 as well for a particular sample. So that is what is repeatability. Reproducibility is to what extent the multiple auditors are able to reproduce the results given by the others, right? So an auditor is able to reproduce the results given by the other auditors is what we would measure as part of the reproducibility metric. So any variation or mismatch would constitute reproducibility variation. So accuracy, as I told you, will compare the auditor results with the SME result. So let us perform the calculation. So you're going to use the manual formula to perform the calculations. And I will also show you how to perform this exercise using or perform the calculations. Exercise has already been done. We have collated the data. So how to perform the calculations using Minitab. So repeatability, we can actually calculate auditor wise. So auditor 1 in one column, auditor 2 the second column. Now, we can visually look at the trial 1 and trial 2 results of both these auditors covering all the 30 samples one by one, and then find out how many mismatches are there, and thereby we would be able to calculate the repeatability variation percentage. So that will be a time consuming exercise, right? So what we can do is we can look at writing a formula in Excel. So this is nothing but your if formula and if and formula. That's it. So these are the formulas that I'm going to use in Excel in order to perform the calculations, right? So for auditor 1, if the trial 1 result for a particular sample unit is equal to trial 2 result, so both the results are same, then count it as 0 because we need the mismatch count. So if there is any deviation, then count it as 1. Right? Close the bracket. So for auditor 1, sample number 1, both the trial results are same. So that is why it has counted as 0. If the trial results were different, then it would have counted as 1, which we will see for auditor 2. Auditor 2, once again, let me write the Excel formula. If the trial 1 result is equal to the trial 2 result, count it as 0, otherwise count it as 1. So it has counted as 1. because there is a mismatch, right, between the trial results for sample number 1 as far as auditor 2 is concerned. Now I can simply copy paste this formula for all the other 29 sample units and straight away get the number of mismatches as far as repeatability is concerned for both auditor 1 and auditor 2 separately. Otherwise, as I told you, if you are going to visually observe and then come out with the number of mismatches, we need to look at the trial 1 and trial 2 results provided by auditor 1 and auditor 2 covering all the 30 samples. That will be a time consuming exercise. So if you know how to write the if formula, it becomes all the more easy. So just copy paste this Excel formula for all the other 29 sample units. That's it, right? So let me count the number of mismatches. So just highlight the column. So we can see the toolbar here, the sum is 7. That means 7 mismatches are there. So auditor 1, as far as repeatability is concerned, 30 checks, out of which there were 7 mismatches. So the matching percentage is only 76.67%, way below the criteria, because variation should be less than 10%, meaning the matching percentage should be greater than 90%. Mismatch percentage should be ideally less than 10% means what? The matching percentage should be ideally greater than 90%. But here we find the matching percentage to be less than 90%, meaning the mismatch percentage or the variation percentage will be in excess of even 20% for repeatability here. So if you want to calculate the number of mismatches for auditor number 2, as far as repeatability is concerned, we again get 7 mismatches. You can see the number here. Sum is 7. So again have 7 mismatches for auditor 2 as well. So both auditor 1 and auditor 2 have performed in the same way as far as repeatability is concerned. Now for calculating the reproducibility, so we need to write the relevant formula. So I will kind of use the next column for calculating the reproducibility. Right. So I'm going to write if and formula in Excel. So if and, right? So in case of reproducibility, as far as this scenario is concerned, all the 4 trial results for a particular sample provided by both the auditors put together should actually match. Even if one of the trial result is different, it would actually constitute reproducibility mismatch. So that's why I told you. So reproducibility, as we can see, is a much more stricter calculation than repeatability. So the repeatability itself has a variation percentage in excess of 20%. The reproducibility variation will be definitely more than that, right? Let us find out. So we use the if and formula. So the trial 1 result of auditor 1 is equal to the trial 2 result of auditor 1. The trial 2 result of auditor 1 is equal to the trial 1 result of auditor 2. The trial 1 result of auditor 2 is equal to the trial 2 result of auditor 2. So all these trial results matches, then count it as 0, otherwise count it as 1. That's it. So if you are going to write a formula like this, then it becomes easy for you to calculate the number of mismatches. Otherwise, we need to look at each and every sample unit and all these trial results and see whether they are matching or not. So let me also calculate the overall variation percentage for repeatability. So this will be 100% minus the matching percentage, which is 76.67%. And you just round it off to 2 decimals. So as we expected, the repeatability variation percentage is 23.33%. So way above the criteria limit of 10%. Fine. So let me just copy paste this formula for all the other sample units and see how many mismatches are there for reproducibility. So let me count the number of mismatches for reproducibility. Here we can see 17 mismatches are there. Out of 30, 17 mismatches are there. So that's why I told you this is a stricter calculation compared to repeatability. So 17 mismatches are there. The matching percentage itself is only 43.33%, meaning the mismatch percentage or the variation percentage will be in excess of 50%. So this will be 100% minus 43.33%. So round this off to two decimals. So we get 56.67% as the mismatch percentage or the variation percentage as far as reproducibility is concerned. So reproducibility variation is 56.67%. Just very, very high, right? So let us also calculate accuracy. Again, accuracy can be calculated auditor wise. We can calculate accuracy for auditor 1, wherein we will compare the auditor 1 trial results with that of the SME result. And we can also calculate accuracy for auditor 2, wherein we will compare the auditor 2 trial results with that of the SME result. So let me again write the if and formula in Excel. If and open bracket auditor 1 trial 1 result is equal to trial 2 result, comma, the trial 2 result of auditor 1 is equal to the SME result. So all these three results matches, then count it as 0, otherwise count it as 1. Right. So let me just copy paste the formula and then count the number of mismatches as far as accuracy is concerned. So how many mismatches? I see 7 mismatches are there. Right. So auditor 1, 30 checks, out of which 7 are mismatches. So the same performance like repeatability, 76.67. Now for auditor 2, again write the if and formula in Excel. If and open bracket, the trial 1 result of auditor 2 is equal to the trial 2 result of auditor 2, comma, the trial 2 result of auditor 2 is equal to the SME result. So all these three results matches, then count it as 0, otherwise count it as 1. So there is a mismatch, right? The trial 1 result provided by auditor 2 for sample 1 is different from the other trial result as well as the SME result. So that is why it has counted as 1. I can just copy paste this formula for all the other 29 sample data points. That's it. Count the number of mismatches. How many are there? 11 are there. So as far as accuracy is concerned, auditor 1's performance seems to be much better than auditor 2. It's comparatively better. We'll not say that auditor 1 has passed the criteria. So auditor 1 has also failed in that criteria. So auditor 2's performance is much worse compared to that of auditor 1. So 30 and 11 mismatches. So only 63.33% is the accuracy level. So if you look at the overall accuracy percentage, it is 70%. So what will be the mismatch percentage? 100% minus 70%, which will be 30%. So if you see all the three measurement system variation matrices, the mismatch percentage or the variation percentage seems to be greater than the criteria limit of 10%. So hence, we cannot trust the data provided by this measurement system. We need to discard the data, correct the measurement system, and collate the data all over once again. So that is what we are supposed to do. So whatever values that we are actually seeing in this exercise file, these are all practical values, right? So compiled from various case scenarios, which I have been part of, right, during my stint with various corporate organizations, right? So all these are practical data. So this is the data taken from one of the Greenbelt project that I mentored way back in 2009. So this is the kind of results that we actually got. But then it presented an opportunity for the project lead to look at the measurement system and then correct the measurement system, right? So that the data provided by that measurement system in the future can be trusted. So we use this Six Sigma project as an opportunity to correct the measurement system. Otherwise, we wouldn't be, or we wouldn't have known that there is some problem with the measurement system and we are not getting the right data. So the accuracy percentage uh, was being continuously, presented to the management in green color, right? So little did the management actually realize that, there could be problem with the data provided by the measurement system. Here, as I told you, the measurement system would comprise of only the quality auditors, right? The discrete data measurement system analysis, the quality inspectors alone will be part of the measurement system. So let me provide the inference. The inference will be, since all the three measurement system variation matrices have the variation percentage in excess of 10% criteria limit, we need to discard the data provided by this measurement system, means provided by these quality auditors, right? Then correct the measurement system, means we need to find out where the auditors are probably lacking knowledge, which part of the process the auditors are probably lacking necessary knowledge. So we need to retrain them, provide them with necessary knowledge, and then look at collating the data all over once again. So correct the measurement system and collate the data all over once again. So this will only result in delay in completion of the Six Sigma project exercise, right? You cannot help it. So that's why I told you, if only you had been, performing this exercise on a routine basis, even when you find that the measurement system is not actually working fine, so there would have been an opportunity for us to correct the measurement system. But during a Six Sigma project, if you find that the measurement system was not actually working fine, and we will not be able to consider the data provided by that measurement system. So we would need to correct the measurement system and collate the data all over once again, which would only result in delay in completion of the Six Sigma project exercise. Right, so this is the inference that we will come up with for this particular scenario where the variation percentage is in excess of the 10% criteria limit. So if you want to perform this analysis using Minitab, so we simply need to copy paste this entire table in the Minitab worksheet. Just copy paste the entire table in this Minitab worksheet, right? So C1 is the sample reference, and the next column, auditor 1, trial 1, auditor 1, trial 2, auditor 2, trial 1, auditor 2, trial 2, and then the final one is the SME result. So I just compiled all these results here after performing the exercise, the gauge R&R, attribute gauge R&R agreement analysis. Now I need to calculate, right? So for that I need to go to stat, and then we have quality tools. Under that we have attribute agreement analysis. So stat quality tools, attribute agreement analysis. So we have data in multiple columns. So choose the option multiple columns. So if you click on the cursor inside this multiple columns field, you can see the cursor blinking here. And you'll also see the columns where you have provided the input values appearing left hand side pane. So we need to enter the auditor provided results here, trial 1 and trial 2 results pertaining to auditor 1 and auditor 2. So auditor 1, trial 1, auditor 1, trial 2, auditor 2, trial 1. and auditor 2, trial 2. So name or number of the appraisers. So we have 2 auditors. So provide the number as 2. Right? So number of appraisers, it will be 2. Number of trials, again will be 2. Right? Because you have only 2 trials for each auditor. So this will also be 2. So appraiser names is optional. So you don't have to really provide the names of the auditors here. So known standard or attribute is the SME result. So we have that, given in this exercise. So we can choose the column where we have compiled the SME result. So you can check on this box and then click OK to get the results. So first we get to see a couple of graphs here. So within appraiser is nothing but the repeatability percentage values, right? So this graph actually depicts the repeatability percentage values for both the auditors. So within appraiser means within a particular auditor. So we'll be ideally comparing the trial 1 and trial 2 results provided by an auditor, right? That is nothing but your repeatability. So keep the cursor on top of this dot for auditor 1. We get to see the overall repeatability percentage, with this 76.67%. And if you're going to keep the cursor on top of the second dot, which would represent the repeatability percentage for auditor 2, so which is again 76.67%. So both auditor 1 and auditor 2 have repeatability percentage of 76.67%, meaning the repeatability variation is 23.33%. Fine. And then the second graph. So what is the second graph here? It says appraiser versus standard. So appraiser versus standard is nothing but comparison of the auditor results with the SME result. So SME result will be considered as the standard result or the true value or the reference value. So this is nothing but the accuracy value. So if you keep the cursor on top of this dot for auditor 1, so you get to see the percentage value as 76.67%. So that is the accuracy percentage for auditor 1. And for auditor 2, keep the cursor on top of this dot, you get to see 63.33%. So 63.33 is the accuracy percentage for auditor 2. So it is perfectly matching with our calculations. Right. So only reproducibility is left out. For that, we need to look at the output section here. So we need to scroll to the top and you'll find between appraisers. So between appraisers would actually represent the reproducibility metric, right? Between appraisers is nothing but reproducibility. So if you see, the matching percentage is only 43.33%. And that is exactly what we also got. 43.33% mismatch percentage or the variation percentage, the staggering 56.67%. Right? So if you look at the kappa value, so it is displayed here for reproducibility, it's a poor 0.36. So I told you if the kappa value is going to be less than 0.75, even for one of the metric, so we need to infer that the measurement system is not working fine and we need to discard the data provided by that measurement system. But here we find for reproducibility, the kappa value is 0.36, which is way below the criteria of 0.75. So here we find for repeatability, so this is accuracy. So accuracy for auditor 1, the kappa value is slightly better, but for auditor 2, the kappa value is only 0.48. Right? And then for repeatability, we find the kappa value to be 0.52 for auditor 1 and 0.5 for auditor 2. Fine. So even the kappa value, if you look at, so we don't see the kappa value to be greater than 0.75, except for the accuracy percentage for auditor 1. Rest of the matrices, the kappa value percentage seems to be less than the criteria limit of 0.75. Fine. So this is how we will perform this measurement system analysis exercise for a discrete data scenario and then come up with the results, right? So we will have a 15-minute break. So when we come back, we'll look at how to perform the measurement system analysis for a continuous data scenario. And we will also work out an exercise under MSA continuous. So that will be after a 15-minute break. Hello, friends. I'm back. Hope you're all back as well. So let us continue with the continuous data measurement system analysis. So let me just share my screen and you'll go back to the notes file. Fine. So this is what I've summarized, all these three matrices, which would actually represent the measurement system variation for a discrete or attribute scenario. The first one is the repeatability. So the repeatability, as I told you, is the consistency of results provided by an auditor for multiple trials for a particular sample. So any mismatch in the trial results provided by an auditor for a sample unit will be considered as repeatability variation. And then the second metric that we have is reproducibility. So reproducibility is nothing but the consistency of results provided by multiple auditors or inspectors for a particular sample. Any mismatch in the auditor or the inspector provided results will be considered as reproducibility variation. And the third metric that we have is accuracy. So accuracy is where we will work out the consistency of the auditor provided results when compared with the true value, the reference value. So this will be my subject matter expert results for a particular sample. So any mismatch between the auditor results and the SME result will be considered as accuracy variation. So all the above three matrices, the mismatch or the variation percentage should be ideally less than 10%. Fine. So now let us look at the continuous data measurement system analysis. So for continuous data measurement system analysis, we need to have minimum of 10 sample units, right, for our exercise. And these sample units are referred as parts here, part 1, part 2, part 3, up to part 10. So I think yesterday or a couple of days back, I would have told you that for a meaningful statistical analysis, so we need to have minimum of 30 sample data points, but there are, exceptions for certain statistical concepts. And this is one such concept where we have an exception with regard to the requirement of the sample units, right? So it's enough if you have just 10 sample units considered for this exercise. So for discrete data measurement system analysis, I told you we need to have minimum of 30 sample units. And yesterday also, when we actually calculated the descriptive statistics measures, or when we constructed the box plot or the histogram, I had told you very clearly that we need to have minimum of 30 sample data points. So minimum of 30 sample data points for a meaningful statistical exercise is a standard one. But then there are few exceptions. For certain statistical concepts, we can also have less than 30 sample data points. So here, continuous data measurement system analysis is one such scenario, wherein it's enough if you have just 10 sample units considered for this exercise, right? So let us assume that we are measuring the weight in kilograms. So here in continuous data, the measurement system would comprise of the measuring equipment and also the appraiser who would be handling that measuring equipment, right? So in case of discrete data measurement system analysis, the entire measurement system would actually comprise of only the quality auditors or the quality inspectors. So continuous data measurement system analysis, since we will be dealing with the measurement data, so we will have the measuring equipment as well as the appraiser who would be handling that measuring equipment in order to measure the unit part as part of the measurement system, right? So here let us assume that we are measuring the weight in kilograms. So we have, as we saw for discrete data, we need to have minimum of two appraisers. Just like how, we told that we need to have minimum of two auditors considered for the discrete data measurement system analysis exercise. So for continuous data, we need to have minimum of two appraisers involved in that exercise. And each appraiser will have to measure a particular sample unit minimum two times. Just like how, we are supposed to have trial one and trial two. So minimum two trials for each auditor. So here again, each appraiser is supposed to measure a particular unit part minimum two times. So appraiser 1 will have to measure minimum 2 times, appraiser 2 will have to measure minimum 2 times. So only when we have minimum of 2 values provided by each appraiser with regard to a sample unit, we will be able to calculate this metric called repeatability variation, right? So if you want to calculate any variation metric, right? So we need to have minimum of 2 sample data points, right? Which is the logic, correct? So if you have only one single data point, we will not be able to calculate the quantum of variation. So if you want to calculate the quantum of variation, or if you want to apply the variation matrices, then we need to have minimum of 2 sample data points. Then only we can calculate the variation, right? So when we have the data set as 1, 2, 3, 4, 5, we can calculate the variation for that data set. But if you have a data point only one, the data point as only one, then we cannot calculate variation, right? So that cannot be done. So we need to have minimum of 2 data points for us to calculate any variation metric. So that is why for calculating the repeatability variation, we need to have minimum of 2 sample measurement values provided by each appraiser. So here let us assume that appraiser 1 has measured as a sample unit 3 times. So we get 3 measurement values from appraiser 1, and similarly appraiser 2 was also measured the sample unit 3 times. So we get 3 measurement values from appraiser 2. So what I've done is I've also calculated the average of the measurement values provided by appraiser 1 for sample unit 1, and also the average of the measurement values provided by appraiser 2 with regard to sample unit 1, right? And I've also come up with the grand average. Grand average is nothing but average of all the 6 measurement values provided by both the appraisers put together. So appraiser 1 has given 3 measurement values. Appraiser 2 has also given 3 measurement values. So all 6 measurement values put together has been considered for grand average, right? So we will also have a reference value here. So this reference value can be obtained when we have the sample unit measured by a master equipment. So this master equipment will be available only in a central laboratory. So we need to go to the central laboratory and then have the sample unit measured by that master equipment, which will be obviously handled by a master appraiser, right? So that value provided by the master equipment will be considered as the reference value or the true value. Just like how you would consider the time displayed by all these electronic gadgets as the true value or the reference value. And in a discrete scenario, we saw the SME result as the true value or the reference value. Similarly, in a continuous data scenario, since we'll be dealing with all these measurement values, so we will have the unit part measured by the master equipment, which will be available in the central laboratory. So if you are talking about weighing scale here, so the master weighing scale will be available in the central laboratory. So we need to take the sample unit there and have the same measured by that master equipment, which would be handled by the master appraiser. And we can get the reference value with regard to weight of that particular sample unit. So if that happens to be 2.56, we have the grand average as 2.57. We can then calculate what is called bias. So bias is the metric which is the equivalent metric for accuracy in discrete data scenario. So here we would call that as bias. So bias is nothing but the difference in the average of the measurement values provided by the appraisers and the reference value, which can be obtained by having the sample unit measured by that master equipment, right? So the bias here in this example, it is 0.01, 2.57 minus 2.56, right? But if you do not have the provision to have the sample unit measured by that master equipment in a central laboratory, then we cannot calculate this metric called bias, and we should be happy with the repeatability and reproducibility variation calculations. That's it, right? That itself is more than sufficient. So if you're not looking at the accuracy part, then we don't have to, have the measuring. We don't have to really get the sample unit measured by the master equipment. So we can simply calculate the repeatability and reproducibility variation alone. But then if you have the sample unit, measured by that master equipment in the central laboratory, we can also calculate the third metric, which is bias. Similarly, the discrete scenario, if you do not have the provision to get the sample units inspected by the subject matter expert, then we cannot calculate the accuracy part. We will be able to calculate only the repeatability and the reproducibility. Clear? So let us look at the various matrices that we would calculate for continuous data measurement system analysis. So as I told you, bias is the difference between the average of the measurement values provided by multiple appraisers for a unit part and the reference value, which can be obtained by having the sample unit measured by the master equipment. And then we have the repeatability variation. So this repeatability variation is also referred as the gauge variation. So gauge, as I told you, would indicate the measuring equipment. So measuring equipment is what we would call as the gauge here, right? So the repeatability variation is nothing but the measurement system or the measuring equipment variation, right? So not the measurement system. Measurement system is a much more wider term. So within the measurement system, we will have the measuring equipment, right? Part of the measurement system. And that measuring equipment is what we would call as the gauge variation. And that is nothing but your repeatability variation. So what is the repeatability variation here? So repeatability variation is nothing but the differences in the measurement values provided by an appraiser when he or she measures the same part using the same gauge multiple times. So again, I repeat. So repeatability variation or the gauge variation is nothing but the differences in the measurement values provided by an appraiser when he or she measures the same part using the same gauge multiple times. So the same part, the same appraiser, when it is measured multiple times, we get different values. Then the differences or the variation in the measurement values that we observe is due to the measuring equipment. So that is why this repeatability variation is called as gauge variation. Clear? Then we have reproducibility variation. So what is reproducibility variation? So this is nothing but the differences in the average of the measurement values provided by multiple appraisers when they measure the same part using the same gauge. So what is reproducibility variation? This reproducibility variation is also referred as appraiser variation. So I told you the measuring equipment and the appraisers will be part of the measurement system as far as continuous data is concerned. So repeatability variation is referred as gauge variation or the measuring equipment variation. Reproducibility variation is referred as appraiser variation, right? So what is this reproducibility variation? This is the differences in the average of the measurement values provided by multiple appraisers when they measure the same part using the same gauge. So that is what we would call as reproducibility variation. So there we actually refer to the metric called repeatability and reproducibility. So repeatability and reproducibility will be referred in a positive sense. That is why we told that the consistency of results will be repeatability or reproducibility, correct? But here we are talking about repeatability variation and reproducibility variation. So we need to look at the differences in the measurement values, right? So this is the difference. So the opposite of repeatability is repeatability variation. And the opposite of reproducibility is reproducibility variation. So that is what I have summed up here. So repeatability variation or the gauge variation is similar to the repeatability that we saw as part of the discrete data measurement system analysis, wherein we would be comparing the trial results provided by an auditor. Similarly, the repeatability variation, which is also referred as the gauge variation or the measuring equipment variation, is the differences in the measurement values provided by an appraiser when he or she measures the same part using the same gauge multiple times. Then what is reproducibility variation? This is also referred as the appraiser variation. So this reproducibility variation is nothing but the differences in the average of the measurement values provided by multiple appraisers when they measure the same part using the same gauge. So that is why we calculate the average of the measurement values provided by an appraiser, right? So this average measure is calculated in order to obtain the reproducibility variation. Fine. But then what is the corrective action that we are supposed to take? So if you happen to find the overall gauge R&R variation for a continuous data measurement system analysis to be in excess of 10%, and if you find the repeatability variation to be significantly higher than the reproducibility variation, then we need to infer that the problem lies with the measuring equipment. And we need to give the measuring equipment for necessary calibration. So we need to give it for repair work, right? So the repair work is what we would technically call as calibration. Clear? So if you have the overall gauge R&R percentage in excess of 10%, which is the criteria limit, and out of the two variation components, if you happen to observe the repeatability variation to be significantly higher than the reproducibility variation, then what is the corrective action we need to take? We need to infer that the problem lies with the measuring equipment because repeatability variation is referred as gauge variation, and we need to give the measuring equipment for necessary calibration. So there can be a question on this. So they will not ask you to perform the exercise, right? In the final assessment, they will not ask you to perform the exercise pertaining to the measurement system analysis, but they will give you a scenario. So in that scenario, you would find the overall gauge R&R variation to be in excess of 10%. It will be something like 21%. And you will also find that the repeatability variation is something like 16%, and the reproducibility variation is less than say 6% or whatever. So this being the case, since the overall gauge R&R variation is in excess of the criteria limit of 10%, so we can clearly infer that the measurement system is not working fine. But that out of the two components which would actually form part of the measurement system as far as continuous data MSA is concerned, which component is actually as actually contributed to the excessive overall gauge R&R variation is the next question. So suppose you find the repeatability variation to be in excess. Here in this particular scenario that I am explaining, so the repeatability variation is significantly higher than the reproducibility variation. So they would have asked you in that question, what is the problem here? So we need to pick the option, the problem lies with the measuring equipment because you find the repeatability variation to be significantly higher than the reproducibility variation. On the other hand, if you find the overall gauge R&R variation to be less than 10%, and they've also provided the repeatability and reproducibility variation percentages, you don't even need to really look at whether one is greater than the other or not, right? Because when the overall gauge R&R variation is well within the criteria limit, we can straight away infer that the measurement system is working fine. So we don't have to really bother about finding out which component of the variation is significantly high. Clear? Right? So there can be another scenario given as a question in the final assessment wherein they would have mentioned the measurement system variation to be less than 10%. So moment you see the overall gauge R&R variation to be less than 10%, then we can straight away infer that there is no problem with the measurement system, right? So the metric that we need to see is gauge R&R variation, right? So it will be given as gauge R&R percentage. That means it is gauge R&R variation percentage. So only if that gauge R&R variation percentage is in excess of the 10% criteria limit, we need to look at whether the repeatability variation or the reproducibility variation has contributed to that excessive overall gauge R&R variation percentage. But if the overall gauge R&R variation percentage itself is less than 10%, then we don't have to bother, right? So we can infer that the measurement system is actually working fine. So that's what is written here. So if the repeatability variation is significantly higher than the reproducibility variation, we need to infer that the problem lies with the measuring equipment, that is the gauge, and we need to provide this measuring equipment for necessary calibration. On the other hand, if the reproducibility variation is going to be significantly higher than the repeatability variation, then what we need to infer? We need to infer that the problem lies with the appraisers. So probably a couple of appraisers involved in the exercise do not know how to handle the measuring equipment. So due to which they have actually contributed to this reproducibility variation. So we need to find out, which appraiser or uh, the group of appraisers who are actually at fault, and we need to retrain them. We need to provide retraining to those appraisers, teaching them how to handle the measuring equipment. So that is the corrective action we will take when we find the reproducibility variation to be significantly higher than the repeatability variation. Clear about this continuous data measurement system analysis exercise? So what we are going to do, we are going to work on an exercise now, and we are going to be completely dependent on Minitab to provide us with the variation percentage results. But before that, we will also work on some preliminary analysis, right, using some descriptive statistics measures, and then try to find out whether repeatability variation is higher than the reproducibility variation or the other way around, right? So at least to that extent, let us kind of uh, come up with the inference. But the actual inference or the final inference, we will be able to know only through the Minitab output, right? So here is one scenario where we would be completely dependent on Minitab to provide us with the final result. So no doubt we can perform some preliminary analysis with the help of the descriptive statistics metrics, but then the final result we need to refer to the Minitab output. So let us look at the exercise. So the below measurements pertain to the time taken in minutes to answer a call in a customer support process. So we have been asked to validate whether the measurement system is actually working fine or not. So here I've already worked on certain matrices. So let me just unhide the columns where the workings have been done, and we will try to interpret. Fine, right? So these are the input values that we have. So we have some 10 transactions. So these are the 10 calls. And we have a couple of agents, the appraisers, who would be measuring each and every transaction with regard to the time taken. And we have two measurement values provided by each agent for a particular transaction, right? So two measurement values are enough, as I told you, for us to calculate the repeatability variation. So we have agent 1 and agent 2. So we have two measurement values provided by each agent for a particular transaction, right? So now what I have done is I have actually calculated some descriptive statistics measures. So I have considered range. So range is nothing but the differences in the measurement values provided by an appraiser or an agent for a particular transaction. So here, when we are calculating the differences in the measurement values for a particular transaction, the range as a descriptive statistic metric would indicate what component of variation, repeatability variation or reproducibility variation. So with whatever we have seen so far, range as a metric would represent which variation, which component of the measurement system variation, repeatability
Repeatability.
variation or reproducibility?
Repeatability.
Repeatability variation. Very good. So repeatability variation, right? Because we are looking at the differences in the measurement values provided by an agent for a transaction. That is what we have calculated as a range, right? So range as a value here would represent repeatability variation. So let me just provide that summary. So range as a metric would represent repeatability variation, right? And I've also calculated the mean values for each transaction, right, pertaining to both the agents. So mean values for each transaction. Mean is nothing but the average of these measurement values provided by an agent for a particular transaction. And I've also calculated the differences in mean. So when we have differences in the average of the measurement values provided by multiple agents, then that variation would be referred as reproducibility variation, right? So the differences in mean as a metric here would represent reproducibility variation. So this is the clarity that we need to have at the beginning. So differences in mean would represent reproducibility variation, right? Now, what is the overall differences in mean? So the average of the differences in mean. So we can simply look at the differences in the overall mean. So 22.5 and 22.8, the difference is 0.3, right? So even if you are going to take the average value with regard to differences in mean, you get average as 0.3. So you don't have to really worry about the sign. You're only looking at the quantum. That's it. So average is 0.3. That is what I've written here, right? So this is the average of differences in mean, which is a meager one. And if you see the individual transactions, the differences in mean is quite significant for transaction number 7 and transaction number 10. So these two are the only transactions wherein we have the differences in mean excess of 1. That means it's quite significant, right? So transactions where differences in mean is greater than 1. So what are the two transactions? As we can see, the 7th transaction and the 10th transaction. So all the other transactions, if you see, the differences in mean is quite negligible. So it's less than 1, it's not much. It's not quite significant, right? It's quite negligible. So only for transaction number 7 and transaction number 10, we seem to have significant differences in the mean value. So these are the only transactions where we have a significant difference in mean value. Now, the similar way, let us calculate the average, the overall average for the range values. So overall average for range. So how will you calculate? So we will sum up all these range values pertaining to agent 1 and the sum of all the range values pertaining to agent 2, right? So how many range values we have considered? So 10 for agent 1, 10 for agent 2. So total of 20 range values have been considered. So for calculating the average, so in the denominator, I will have 20. So the overall average for range comes out as 1.14. Now I can find out how many transactions pertaining to agent 1 we have range values in excess of this overall average. That means above average. Because range as a metric is lower the better kind of metric, right? So all these variation matrices, we need to have minimal value. So we will try to find out which of the transactions pertaining to agent 1 we have the range values in excess of the overall average of 1.14, right? So agent 1 transactions where range is greater than 1.14. So how many transactions are there? So here first transaction is fine, second is fine, third is fine, fourth is fine, fifth is also fine, sixth transaction 1.8 is the range. Eighth transaction 1.9 is the range. 10th transaction 1.5 is the range. So 6, 8 and 10 are the three transactions pertaining to agent 1 where we have range values in excess of the overall average of 1.14. So 6, 8 and 10, right? Similarly for agent 2, let me find out how many transactions we have the range value greater than 1.14. So let me look at the range values for agent 2. So the first transaction is fine, second is fine. Third transaction, we have a range value 1.3. Fourth transaction, we have a range value in excess of 2. So we didn't see any range value in excess of 2 for agent 1. For agent 2, we are seeing a range value in excess of 2. So 2.1. So third transaction, fourth transaction, and then the sixth transaction, seventh transaction, eighth transaction, ninth transaction. So many transactions. So 3, 4, and then 6, 7, 8, 9. So many transactions for agent 2. So 3, 4, 6, 7, 8, 9. Right? So three transactions for agent 1 where we have range values excess of 1.14 and 6 transactions pertaining to agent 2 where we have range values in excess of 1.14. So looking at this, we can clearly understand that the repeatability variation seems to be much higher than the reproducibility variation because the differences in the mean is only 0.3. But if you look at the average of range, right, which would represent the repeatability variation, it is 1.14. And we have so many transactions pertaining to both the agents where we have the range values in excess of this overall average of 1.14. In fact, for agent 2, we have some three transactions where the range values are in excess of 2. So we can clearly understand, right, that the repeatability variation, so which is represented by this metric range, seems to be much higher than the reproducibility variation represented by differences in. So the inference of the preliminary analysis. The range as a measure seems to be significantly higher than differences in mean. Hence, repeatability variation seems to be significantly higher than the reproducibility variation. Right? So this is the preliminary result, preliminary analysis result. But then we need to calculate the overall gauge R&R variation, right? We need to take the help of Minitab, and we also need to look at, the exact repeatability variation and the reproducibility variation. But one thing that is 100% sure, we will have a scenario in case the overall gauge R&R variation is exceeding the criteria limit of 10%, then we will have a scenario wherein the repeatability variation will be significantly higher than the reproducibility variation. So you'll also validate that, right, by performing the exercise using Minitab. Fine. So if you want to use Minitab, we need to arrange the data in a vertical structure. So here we find the data arranged in a horizontal structure. So we need to have the data arranged in a vertical structure, right, for each transaction. So I'm just going to use the transpose function in Excel to arrange all these data points in a vertical structure. So one below the other, right? So it'll keep continuing like this. The second data point. Then the third data point. The fourth transaction. And then the fifth transaction. Let me copy paste all these values pertaining to first five transactions. The balance five transactions we will copy paste later. So for that, let me just erase this discrete data MSA input values. And then in column number 3, let me copy paste all these time measurements. So when I have arranged the first five transaction values in a vertical structure, we will have total of 20 values, because for one transaction we have 4 measurement values provided by both the agents put together, right? So for 5 transactions, 5 into 4, we will have 20 measurement values. So let me find out if we have filled in all the 20 rows. Yes, right? So we need to continue from the 21st row. So let me just erase this and I will continue from the 6th transaction. And then the 7th transaction. Then the 8th transaction. And then the 9th transaction. Then the final transaction. So how many data points we will have in total? So 20 plus 20, 40 data points, right? So we have 10 transactions. As I told you, each transaction, we will have 4 measurement values provided by both the agents put together. So we will have total of 40 values, measurement values. So let me copy paste the second set of 20 measurement values. So I will continue from row number 21 here. So if you scroll down to the end, you will see all the 40 rows have been filled in as far as the time values are concerned. Fine. Now, what I need to do, I need to provide the transaction reference in the first column, right? And I need to provide the agent reference in the second column. So if you're providing the transaction reference, I can understand that the first 4 data points pertain to transaction number 1, right? So 2 measurement values provided by agent 1, followed by 2 measurement values provided by agent 2. So that is how we have arranged. So the first 4 transactions or the first 4 measurement values pertains to transaction number 1. The next 4, transaction number 2. Then transaction number 3, transaction number 4, transaction number 5, transaction number 6, transaction number 7, transaction number 8, transaction number 9, and transaction number 10. So this is how we need to arrange the data. So we cannot simply copy paste the table. So we just need to arrange the data like this in order to perform the analysis. Now we need to provide the agent reference. So for each transaction, the first 2 data points pertains to agent 1 and the next 2 pertains to agent 2. So for transaction number 1, if you see, the first 2 measurement values belongs to agent 1, the next 2 belongs to agent 2. So the same sequence will continue for all the 10 transactions, right? So we will have the same sequence for all the 10 transactions. So I can just copy paste. Ninth transaction, the final one, 10th transaction. So I filled in all 40 rows for all these 3 columns, right? So the data is ready for analysis. So for continuous data measurement system analysis, in order to obtain the overall gauge R&R variation percentage and also the repeatability and reproducibility percentage values. So we need to again go to stat and then the quality tools. Under that we have gauge study. So stat, quality tools and gauge study. So we will choose gauge R&R study crossed. So part numbers is nothing but the transaction reference. So double click on that column header so that it appears inside this field. Operators is nothing but the agent reference. Measurement data is the time data. So we can have the method of analysis as ANOVA. So we will learn what is this ANOVA exercise in the analyze phase. And we can retain the ANOVA method of analysis for this scenario. And we can straight away click OK. So you will get to see some 6 graphs. So how to interpret, right? So the first graph will actually provide you with the measurement system variation values. So for that, we need to look at the bars which are colored in green color. So the green color bars would provide us with the measurement system variation values. So the overall gauge R&R variation, if you keep the cursor on top of this green color bar, so it provides a value 31.28%, which is way above the criteria limit of 10%. So let me also provide the Minitab output values here. So as per the Minitab output, so the gauge R&R variation is 31.28%. And then we have repeatability variation and reproducibility variation, right? So what is the repeatability variation? Let us see whether the repeatability variation is significantly higher than the reproducibility variation or not. So if you keep the cursor on top of this green color bar, right under repeatability, so we find the bar value to be 30.98%. So we can clearly understand that the repeatability variation seems to have contributed to this excess overall gauge R&R variation. And that was our preliminary analysis finding as well. So reproducibility variation, the third one, right? So it's quite negligible. So keep the cursor on top of this. So you find the bar
बंद क्यों नहीं
value.
कर दिया हूँ?
Yes. Can you just please go on mute? You're not asking any question. So the value is 4.28%, right? So the reproducibility variation is 4.28%. And this is what we inferred, when we performed the preliminary analysis, we could find that the repeatability variation was significantly higher than the reproducibility variation. And the overall gauge R&R variation also seems to be much higher compared to the criteria limit of 10%, less than 10%. So let us go back to the graph. Let us look at the second one. So the first graph itself has provided us with the final result, right? But then let us also try to interpret the other graphs. How come the repeatability variation is significantly higher than the reproducibility variation? So this is the R chart or the range chart. So pertaining to both the agents, agent 1 and agent 2. So the first half contains the range value plottings for all the 10 transactions for agent 1. The next half provides the range plottings for the 10 transactions pertaining to agent 2, right? So if you see R bar, which is the overall average of range, is given as 1.14, and that is exactly what we also got, right, using the manual formula. And if you look at the transactions above this average of for range, so we have three transactions pertaining to agent 1, where we have the range values in excess of 1.14. So keep the cursor on top of these data points. So this is sample number 6, sample number 8, and sample number 10. So these are the three transactions pertaining to agent 1, where we have the range values in excess of 1.14. And similarly, if you see for agent 2, so third transaction, fourth transaction, sixth, seventh, eighth, ninth. So 3, 4, 6, 7, 8, 9. So these 6 transactions, we have the range values in excess of 1.14 for agent 2. So the range chart clearly demonstrates that whatever, you know, uh, output that we actually got by performing the preliminary analysis, the same output is reflecting here as well. Now, moving on to the X bar chart. So X bar chart is nothing but the plotting of mean values, right? X bar is the sample notation for mean. So X bar chart is the plotting of mean values. So similar to the range chart, we have the chart divided into two sections. The first half contains the mean values pertaining to agent 1, and the second half contains the mean values pertaining to agent 2. So if you look at the mean value trend pertaining to all the 10 transactions, so we find agent 1 and agent 2 having a similar trend. That means there is no significant difference in the mean values for agent 1 and agent 2. So except for the 7th transaction, we see for agent 1 is showing a downward trend, whereas for agent 2 it is showing an upward trend. And similarly for the 10th transaction, for agent 1, the slope is not all that steep, whereas for agent 2, the slope is very, very steep. And this is better illustrated when we actually superimpose these two mean trends pertaining to agent 1 and agent 2 on top of each other. So when you actually superimpose the mean trend charts pertaining to both agent 1 and agent 2 on top of each other, so we see the trend is matching perfectly for most of the transactions, indicating that the differences in mean is not all that significant, except for transaction number 7, where we find a significant gap, right, between the trend chart of agent 1 and trend chart of agent 2. Similarly, if you look at transaction number 10, we again see some significant gap between the two trend charts. So that is exactly what we also inferred in our preliminary analysis. So the transactions where the differences in mean is quite significant are 7 and 10. So these two are the only transactions where we have the differences in mean in excess of 1. All the other transactions, the differences in mean was less than 1. It was not all that significant. So this itself clearly tells that the repeatability variation is significantly higher than the reproducibility variation. Now moving on to the next one. So this is actually individual plotting, right? The plotting of individual data points pertaining to both agent 1 and agent 2 covering all the 10 transactions. So if you see the agent 2 plotting seems to be higher in length compared to that of agent 1, indicating that agent 2 has exhibited higher variation compared to that of agent 1. So agent 2, if you see the range of the data points seems to be significantly higher compared to that of agent 1. And that is what is proving out to be, right? So agent 2 has range values in excess of the average of 1.14 for 6 transactions. In fact, out of these 6 transactions, 3 transactions, we have the range values in excess of 2. So agent number 2 has contributed to this repeatability variation significantly compared to agent number 1, right? And that is what is getting demonstrated here when we see the individual plotting of data points pertaining to both agent 1 and agent 2. So this is similar to a box plot. So if only we had constructed a box plot, we can find that the box plot for agent 2 would have been lengthier compared to that of agent 1, indicating that the variation contributed by agent 2 is significantly higher than that of agent 1. So we know that the repeatability variation is very high, but out of the 2 agents, who has a higher repeatability variation? It is agent 2. And the final graph again will help us to kind of show the trend, right, pertaining to all the 10 transactions, right? So these are the measurement values of both the agents put together. So the individual measurement values are there, but we also found out the overall mean for each transaction. And for that overall mean, we have actually constructed this trend chart, right? So this is how we need to interpret, right, all these graphs. So let me just copy paste this graph in the exercise file, right? So this is about continuous data measurement system analysis. You can even refer to the output section, right? So you scroll down, so you can find what is called as percentage study variation. So this percentage study variation is the metric which we need to consider for the gauge R&R variation as well as the repeatability and reproducibility variation. So the total gauge R&R variation, we have the percentage study variation as 31.28%, and the repeatability component, we have the percentage study variation as 30.98, and the reproducibility component, we have the percentage study variation as 4.28. So the overall gauge R&R variation is in excess of the 10% criteria limit. And if you look at the component of variation, which is contributing to this overall higher gauge R&R variation, it is the repeatability variation, right? So when we compare the repeatability and reproducibility variation, it is like chalk and cheese, correct? So the repeatability variation seems to be significantly higher than the reproducibility variation. So what is that? We can infer through this. So since the repeatability variation is higher than the reproducibility variation, we need to infer that the problem lies with the measuring equipment, and we need to provide the measuring equipment for necessary calibration. So let me also provide that inference here. So what will be my inference? Since the overall gauge R&R variation is in excess of 10% criteria limit, and the repeatability variation is significantly higher than the reproducibility variation, we need to infer that the problem lies with the measuring equipment. So what is the corrective action we are supposed to take? So we need to give the measuring equipment, which is what we would call as gauge. So technical language is gauge. So we need to give the measuring equipment for necessary calibration. Right? So this will be my corrective action. So this is how we'll come up with the inference. As I told you, you can get some 3 or 4 questions pertaining to this measurement system analysis. So the first question could be like the overall gauge R&R variation would have been given in excess of even 20%, and you would find the repeatability variation to be significantly higher than the reproducibility variation in that case scenario. And they will ask you to find out what is the problem. So we need to pick the option. The problem lies with the measuring equipment or the gauge, right? So there will be another question wherein the measurement system, overall measurement system variation will be less than 10%. And they would have also given the repeatability and reproducibility percentage values. So moment you find the overall gauge R&R percentage to be less than 10%, we can infer that the measurement system is actually working fine. There are no issues with the the measurement system, right? So that is the option that we need to pick for this second scenario where the overall gauge R&R variation is less than the 10% criteria limit. The third scenario, so they would have given some multiple auditors involved in the exercise. So we are measuring or we are procuring the measurement values provided by these multiple appraisers. So what is that? We are trying to establish here. So when we want to compare the measurement values provided by multiple appraisers, right, in this measurement system analysis exercise, we are actually trying to establish the reproducibility variation. So reproducibility is the correct option that we need to pick for this scenario. So when we find multiple appraisers involved and we are comparing the results provided by these multiple appraisers, then what is that we are trying to establish here? We are trying to establish the reproducibility variation. So reproducibility is the right option that we need to pick for this particular question. So these are the 3 questions that we can get, right, with regard to the continuous data measurement system analysis. Fine. So let us stop here because the next topic that we are going to look at is also an important topic called probability distribution. So this probability distribution, somewhat an advanced topic, but then we will try to make it simplified. So we got some, some good case scenarios which we will work tomorrow. But since this is an important concept in the measure phase, so we will not discuss this uh, today. So we will look at it fresh tomorrow, right? So maybe, after the revision is done, in case there is some time available, so we will just get introduced to this probability distribution concept. So we'll not go deep into it, right? So today, let us not go deep into the probability distribution. We will probably look at the concept at a very high level, but then tomorrow we'll start working on the exercises under probability distribution. Fine. So let us do a quick revision of whatever we covered today. So we looked at the 4th exercise in the descriptive statistic sheet, wherein we were asked to compare the performances of 2 different branches of a bank, and the metric that was given was the time taken to open a bank account. So obviously you would want to calculate the average time taken to open a bank account, which is what we would call as a mean. So if you are dealing with continuous data and you are calculating the average, that is what we would call as mean, right? So the mean time taken to open a bank account was obtained for both the branches. But then we could find that the mean time was pretty much similar for both the branches. So the mean is similar, the average performance is the same for both the branches. And the next metric that we need to consider is the variation metric. It's because we would want to find out now that the average performance is pretty much similar. So we would want to find out which category is providing a consistent performance. And for that, we would calculate the variation metric, right? So the variation metric will actually indicate the extent of inconsistency that we observe in the process performance, right? So that is exactly what we did. So we calculated the standard deviation for both the branches. So this is the standard deviation with regard to the time taken to open a bank account for both these branches, branch A and branch B. And we could find that the branch B has a lesser standard deviation compared to branch A. So indicating that branch B's performance is much more consistent compared to that of branch A, and hence we will infer that the branch B's performance is better than that of branch A. And we can also construct the box whisker plot, the multiple box whisker plots for both the branches. And here it clearly demonstrates that branch B's performance is highly consistent compared to that of branch A. So blue color box whisker plot would actually pertain to branch A and the red color one for branch B. So if you compare the length of the box whisker plot, we could find that for branch B, the length of the box whisker plot is significantly lesser compared to that of branch A, indicating that branch B is exhibiting lesser variation compared to that of branch A. So the length of the box whisker plot will indicate the variation exhibited by that category. So what we can understand through this is box whisker plot as a tool will also help us to logically subgroup discrete x's. So here discrete x's are branch A and branch B against continuous y. So the continuous y is nothing but the time taken to open a bank account. So that is another benefit that we would get when we construct the box whisker plot for multiple categories, right? And then we looked at the concept of yield, right? So yield as a term refers to the output that is produced by a process, right? That is generated by a process. And obviously this output will be free of any defect. That means even if there is any defect, it would have got corrected. Then only you'll consider that as yield. But then we have what is called throughput yield. So this throughput yield is nothing but the first pass yield generated at a sub-process level. So if you have a process, then within that we will have multiple sub-processes. So throughput yield is nothing but the first pass yield generated at a sub-process level. And then finally, we can calculate the roll throughput yield, which is nothing but the first pass yield generated at a process level. So even before the correction is done, so we will be calculating the first pass yield. So through roll throughput yield is nothing but the first pass yield generated at a process level, right? And we also looked at an exercise and saw how to calculate the roll throughput yield. So if you want to apply the manual formula, as I told you in the final assessment, the question itself, they would have provided the throughput yield values in terms of percentage. So what we need to do in order to calculate the roll throughput yield, we need to convert these percentage throughput yield values in terms of decimals and then simply multiply them irrespective of the number of sub-processes. So once we have converted the percentage throughput yield values in terms of decimals, we simply need to multiply them in order to arrive at roll throughput yield in terms of decimal, and that decimal RTY value can be expressed in terms of percentage as well, right? But then I also showed you how to use my template to perform this RTY calculation. But then the template will, or the template can accommodate only up to 4 sub-processes, right? So if you have the fifth sub-process given in the exercise or given in the question, then we cannot use the template. But the calculation, as I told you, is very, very easy, right? So we simply need to convert the percentage throughput yield values in terms of decimals and multiply them to arrive at roll throughput yield in decimal. And that decimal RTY value can be expressed as a percentage value, right? It's a simple calculation. So couple of problems will be uh, they are part of the final assessment pertaining to RTY calculation. So one problem will appear in the green belt final assessment. So another problem will appear in the black belt final assessment. So both for RTY calculation. And then we looked at a very, very important concept called measurement system analysis. In short, it is referred as MSA. So measurement system analysis is a very important exercise that we are supposed to perform on a routine basis, not just at the time of working on a Six Sigma project exercise. And in fact, measurement system analysis will be the first exercise that we would perform as part of the measure phase, right? So if you are going to perform this measurement system analysis exercise on a routine basis, then as I told you, when we perform this exercise as part of your Six Sigma project exercise, we will not face any surprises. So the measurement system will continue to function well. But if you are going to perform this measurement system analysis exercise for the first time, when we work on a Six Sigma project, then there is every possibility that the measurement system may actually fail. So in that case, we might have to discard the data provided by that measurement system. We need to correct the measurement system and collate the data all over once again, right? So which would only result in delay the completion of the Six Sigma project exercise. Then how to find out whether the measurement system is working fine or not? So we need to refer to the variation contributed by the measurement system. So if you look at the output data set, so the variation in the output data set would be a combination of both the process variation as well as the measurement system variation. So in our Six Sigma project, our effort or our focus will be to reduce the process variation. And for that, we need to ensure that the measurement system variation is as minimum as possible, right? So the criteria limit is the measurement system variation should be ideally less than 10%. And the discrete data measurement system analysis, the quality inspectors alone will form part of the measurement system. And the discrete measurement system analysis is also referred as attribute age R&R agreement analysis. So in discrete measurement system analysis, we will conduct the exercise by considering minimum of 30 sample units. And these 30 sample units will be a proper mix of both defective as well as non-defective samples. And we will engage minimum of 2 auditors or 2 quality inspectors for this exercise. And each auditor or quality inspector will be provided with couple of trials. So these are the minimum numbers that we need to consider for performing the exercise. So we can have more than 2 auditors involved in the exercise, and we can also have more than 2 trials for each and every auditor, right? So these are the minimum numbers. So once we perform this exercise and collate the auditor results, we will also parallelly collate the SME result, because the SME result or the subject matter expert result is to be considered as true value or the reference value in order to measure the accuracy of the auditor provided results. And there are 3 matrices which we would calculate, and the variation percentage of these 3 matrices would indicate the measurement system variation. So the 3 matrices are repeatability, which is the consistency of the results provided by an auditor for multiple trials and for a particular sample. So any mismatch in the trial results provided by an auditor would constitute repeatability variation. And then the reproducibility is the consistency of results provided by multiple auditors for a particular sample, and any mismatch in the auditor provided results for a sample unit would constitute reproducibility variation. And the third one is the accuracy, which is the consistency of the auditor provided results when compared with the true value or the reference value or the subject matter expert result. So any mismatch between the auditor provided results and the true value would constitute accuracy variation. So all these three matrices, as I told you, the variation percentage should be ideally less than 10% for us to infer that the measurement system is working fine. But if any of the measurement system variation metric has a variation percentage in excess of 10%, then we need to infer that the measurement system is not working fine and we cannot trust the data provided by that measurement system. And as I told you, all these three matrices have got some strong linkage. So even if one of the metric has a variation percentage in excess of 10%, it's quite likely that the other two matrices also will have the variation percentage in excess of 10%, right? So we also would look at a metric called kappa value when we perform this analysis using Minitab. So the kappa value should be ideally greater than 0.9 for all the three measurement system variation matrices. If the kappa value is between 0.75 and zero point 0.9, we can marginally accept the data with necessary approvals provided by the leadership team. On the other hand, if the kappa value is going to be less than 0.75, then we need to discard the data provided by that measurement system, correct the measurement system, and collate the data all over once again, right? And we also looked at the continuous data measurement system analysis. So in continuous data measurement system analysis, it's enough if we have just 10 sample units for the exercise. So 10 sample units, and we need to have minimum of 2 appraisers who would be handling the measuring equipment. So in continuous data measurement system analysis, we will have both the measuring equipment and the appraiser as part of the measurement system, right? So again, we will measure some three matrices here, which would represent the measurement system variation. The first one is bias. So bias is nothing but the differences in the average of the measurement values provided by the multiple appraisers and the reference value. So this reference value or the true value with regard to the measurement dimension can be obtained when we have the sample unit measured by the master equipment, which will be available in the central laboratory. So if you don't have access to that master equipment, then we cannot calculate this metric called bias. We need to calculate only the repeatability variation and the reproducibility variation. So in continuous data MSA, the repeatability variation is also referred as the gauge variation or the measuring equipment variation. So this is nothing but the differences in the measurement values provided by an appraiser when he or she measures the same part using the same gauge multiple times. And then the reproducibility variation is also referred as the appraiser variation. So reproducibility variation is nothing but the differences in the average of the measurement values provided by multiple appraisers when they measure the same part using the same gauge. But then if the overall gauge R&R variation is in excess of 10%, and if you find the repeatability variation to be significantly higher than the reproducibility variation, then we need to infer that the problem lies with the measuring equipment and we need to provide the measuring equipment for necessary calibration. On the other hand, if you observe the overall gauge R&R variation to be in excess of 10% and the reproducibility variation is significantly higher than the repeatability variation, then we need to infer that the problem lies with the appraisers. So we need to find out which appraiser is not handling the measuring equipment in a proper way, and we need to retrain that particular appraiser. And we also worked out an exercise pertaining to continuous data measurement system. Right? So I hope you had a very good revision of all these concepts that we saw today. Slightly advanced, but then we try to make it as simple as possible. I hope that things are clear. The main thing is not the calculation part. So we need to know how to take the decisions, right? That is the main thing. So calculation, we can use the simple manual formula, we can use Minitab to get the final result. But the main thing here is how to interpret these results, right? Fine. So as I told you, just get introduced to the probability distributions, but then we will look at this particular concept in detail tomorrow. So probability distribution, again, we are going to restrict our learning to only those which are required as part of the Six Sigma curriculum. So we are not going to go beyond that, because probability distribution again is a very vast subject in statistics, right? So we are not going to go beyond uh, with regard to the statistical concepts under probability distribution. We are going to restrict ourselves learning only those which are required as part of our Six Sigma curriculum. So first and foremost, let us try to dissect this terminology, probability distribution. So what is probability? So as we can see, probability is the chance of occurrence of an event, right? Probability is the chance of occurrence of an event, and distribution is the signature of a data set. So if you have a data set, so this data set will always follow a certain distribution. So distribution is the unique signature of a data set. A data set can follow a distribution, right? So probability is the chance of occurrence of an event, whereas distribution is the signature of a data set, right? So when we talk about probability, so you'll always, give the example with regard to toss of a coin. So when you toss a coin, what are the two options that we can get as a result? So we can either get a head or a tail. So if you are going to toss the coin for the first time, so what is the probability of getting a head or probability of getting a tail? So it will be 50-50% because only two options that we can get as a result. So when we are tossing the coin for the first time, the probability of getting a head is 50%, probability of getting a tail is 50%. So you have another scenario wherein there are three marbles inside a basket. So there is a white marble, there is a red marble, there is a yellow marble, right? Now, without even looking inside the basket, if you are going to put your hand inside the basket, what is the probability that you will pick the white color marble? So it will be 1 divided by 3. There's only one white color marble out of the three marbles inside the basket. So the probability of picking the white color marble will be 1 divided by 3, which will be 33.33%, right? So when we had only two options, the probability of picking a particular option will be 50%. But when we have three options, the probability of picking a particular option will be 1 by 3, which is 33.33%. But then when we have four options, say for example, your multiple choice questions, right? Suppose a student has not prepared at all. So he is just going to answer all the questions by fluke. So if he is going to kind of answer a multiple choice question wherein there are four multiple options given for a particular question, what is the probability that he will end up choosing the right answer out of the four multiple choices? It will be 1 divided by 4. So out of the four multiple choices, we can understand only one will be the correct option. Rest three will not be the correct option. So the probability of picking the correct option when we have four multiple choices it will be 1 divided by 4 or 25%. So even if someone has not prepared for the exam, if he is going to answer all the questions by fluke, by chance, the probability of answering a particular question correctly will be 25%, right? So only 25% chances are there that the person will pick up the correct option for a multiple choice question, right? So what we can actually gather through this is, as we keep increasing the number of options, the probability of picking the right option will actually keep decreasing. When we had only two options for a result, the probability of picking a particular option was 50%. When we had three options, right, for a result, the probability of picking a particular option got reduced to 33.33%, which is 1 by 3. When we have four options for a result, the probability of picking a particular option will get reduced further. It will become 1 by 4, which will be 25%. So as we keep increasing the number of options, the probability of picking a particular option will get reduced, right? So this is something that we need to understand. This is what we would call as estimating probability by chance. Estimating probability by chance. But then as part of our statistical exercises, we are going to solve the probability of occurrence of a particular event when we have some historical performance provided for a case scenario. So based on the historical performance, we will be asked to estimate the probability of occurrence of certain number of events. Say for example, you are asked to estimate the probability of getting some 5 defectives out of say 200 samples. But then you would have been provided with the defective proportion as the historical performance value, right? So the historical performance value would have been given in terms of the defective proportion. So given this historical performance, what is the probability of getting 5 defectives out of 200 samples? So the historical performance was really good. Then the probability of getting even these 5 defectives out of 200 samples will be very, very less. But the historical performance was bad. So the probability of, or the defective percentage or the defective proportion is way too high. Then the probability of getting 5 defectives out of 200 samples will also be very high, right? So it all depends on the historical performance value. So based on that, we will be estimating the probability of occurrence of certain number of events. So this is how the exercises are going to be, right? So we will solve all these probability exercises based on the historical performance value, which would be given as part of the case scenario. Clear? So if you look at the probability distributions, as I told you, distribution is nothing but the signature of a data set. So if you have the data set containing the proportion values of a binary discrete scenario, then the data set would follow what is called binomial distribution. So there are a couple of discrete data probability distributions. So if you have the proportion values of a binary discrete event as a data set, then the proportion values data set would follow what is called binomial distribution. So that signature of that proportion values data set will be binomial distribution. But then if you have a count discrete data set, right? So we have the data set containing the number of units processed or the data set containing the number of defects. So if you have a count discrete data set, then that data set would follow what is called Poisson distribution, right? So two discrete data probability distributions. So the proportion of a binary discrete event, the data set would follow binomial distribution. So that is why it is written as binary discrete data would follow binomial distribution, and proportion is the primary metric for representing binomial distribution. We all know binary discrete data can be better represented by this metric called proportion, which is a derived value. Similarly, when we talk about Poisson distribution, count discrete data would follow Poisson distribution. So if you have a data set containing the number of units processed, or if you have a data set containing the number of defects, etc. So this will be a count discrete data set, and this count discrete data set would always follow Poisson distribution. And what is the primary metric for representing count discrete data? So it is average denoted by lambda, right? Average denoted by lambda is the primary metric for Poisson distribution as well. So you'll be looking at exercises under binomial distribution as well as Poisson distribution under discrete data probability distributions. But then continuous data probability distribution, we are going to look at a famous distribution called normal distribution, right? So normal is the most famous continuous data probability distributions. But then we have host of other continuous data probability distributions as well. So apart from normal, we have Weibull distribution, exponential distribution, uniform distribution, Erlang distribution, Pareto distribution, log normal distribution, so many other continuous data distributions. But all these continuous data distributions which are not normal will be called as non-normal distributions, right? But as part of our curriculum, we are going to look at this normal distribution as part of under continuous data probability distributions. And as we all know, the normal distribution will be represented by a symmetric bell curve. So whenever we draw a symmetric bell curve, it would denote normal distribution. Just like how we have proportion as the primary metric for binomial distribution, average denoted by lambda as the primary metric for Poisson distribution. For normal distribution, we have two matrices, mean and standard deviation. So these two are the primary matrices for representing normal distribution, right? So initially we look at the discrete data probability distributions, both binomial and Poisson, and we will also work out exercises under them. And then we will move on to the normal distribution. So first we will look at the concept of normal distribution, and then we will look at the exercises under normal distribution. So when we discuss about the normal distribution, we are also going to learn how to calculate the sigma level. Because as I told you, at the end of the measure phase, we will arrive at the baseline sigma level of the process performance. So we will not only calculate the baseline CTQ metric performance. So CTQ metric would be the metric representing the business problem, which would help us to quantify the business problem. So we would not only arrive at the baseline CTQ metric performance, we will also have that CTQ metric performance converted in terms of sigma level. So we will also have the baseline sigma level derived at the end of the measure phase, right? So we will also learn how to calculate the actual sigma level for a process performance, which is normal. So under normal distribution, right? So all these things we'll look at tomorrow. So tomorrow also we are going to solve some good number of statistical exercises. Anyway, I have provided templates for all these statistical exercises, so no need to worry. So even if you find the calculation logic to be slightly difficult to understand, we can very well make use of the templates, right? Fine. So let us stop here. So we will continue with our discussions tomorrow. And if there are no questions, we can close the sessions. Fine. So we will close the session. So we will connect at the same time tomorrow evening. So have a good night and thanks for your time today.
Sure. Thank you.
Thank you, sir.
Thank you.